Wherever you are right now, the ceiling above you, or the sky beyond it, is facing outward, facing the rest of it. The part most people never think about, not because it is hidden, but because Neptune was always a reasonable place to stop. 8 planets, a sun at the centre. The solar system more or less accounted for. But Neptune is not an ending. It is more like a doorway that nobody bothered to open for a long time. Welcome to the Sleepy Physicist. If you found this channel, you're probably the kind of person who lies awake thinking about things like this. Distances that don't resolve into images, scales that resist imagination. This is a space built for exactly that. For those of you who come back regularly, who leave comments in the quiet hours, who share this with someone who needed rest, this is yours too. If tonight's the first time you're here, there's nothing to catch up on. Just settle in. Tonight the topic is the Kuiper belt, not as a fact to be filed away, but as a place, a region. Something that exists whether or not anyone is currently thinking about it, which for most of human history no one was. Start with the Sun, not as a star among stars, but as a gravitational body with reach. Its gravity doesn't end at Neptune. It continues outward, weakening with distance according to a relationship that is precise and unforgiving, force decreasing with the square of distance, until eventually, far enough out, the Sun's influence becomes indistinguishable from the background pull of everything else in the galaxy. That boundary is called the heliopause, and it is far. But before you reach it, before the Sun's solar wind finally gives out and the interstellar medium takes over, there is something else. The Kuiper belt begins roughly 30 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. 30 of those, that is where the belt starts. It extends to perhaps 50 astronomical units, maybe a little further depending on how the boundary is defined, which is, it turns out, not entirely settled. In that band of space, the one that begins past Neptune and extends outward for another 20 astronomical units, there are objects, thousands of them that we have catalogued, hundreds of thousands, perhaps more, that we have not. Frozen bodies, rocky bodies, combinations of both, ranging in size from grains and pebbles to Pluto, which is roughly 2,300 kilometers across, and counts by current definitions as a dwarf planet. The belt is not a dense field. If you were travelling through it, you would likely see nothing nearby at any given moment. The objects are real, but the space between them is vast enough that the belt reads visually as emptiness. This is one of the things that makes it difficult to hold in mind. It is a populated region that would not look populated from inside it. The material in the Kuiper belt is old. Not old in the way that rock formations or ancient forests are old. Old in the sense that it formed during the first few million years of the solar system's existence, when the Sun was still settling, when the planets were still accumulating mass from the same cloud of gas and dust that produced everything here. The outer solar system cooled quickly. At those distances from the Sun, temperatures were low enough for volatile compounds, water, methane, ammonia, to freeze into solid form almost immediately, and once frozen there was little to disturb them. The inner solar system was chaotic. Collisions were frequent. Surfaces were reshaped by impacts, by volcanic activity, by the presence of liquid water and atmospheric erosion. The Kuiper belt experienced none of that. The objects there formed and then more or less persisted. They were nudged by gravity. Some were scattered outward into more distant orbits. Some were pulled inward toward the Sun, where they eventually became comets. But the belt as a structure, as a region, remained. What that means is difficult to fully account for. The material sitting in those orbits today carries a chemical memory of conditions that no longer exist anywhere close to here. The solar system's early state is gone from the inner planets, burned off, melted, reworked. But it is preserved imperfectly in frozen bodies drifting 30 to 50 astronomical units from the Sun. Imperfectly is probably the right word. Perhaps preserved is too strong. Some of those surfaces have been altered by radiation over billions of years, by occasional impacts, by slow outgassing of volatile material. But the alteration is shallow compared to what happened closer in. The belt was theorized before it was observed. Kenneth Edgeworth suggested in 1943 that the region beyond Neptune was likely populated with small bodies, material left over from the solar system's formation that never coalesced into a planet. Gerard Kuiper made a related argument in 1951. For decades, the idea existed as a hypothesis without direct evidence. The first confirmed Kuiper belt object beyond Pluto, designated 1992 QB1, was discovered in 1992. After that, the discoveries accelerated. The belt went from theory to demonstrated fact within a few years, and it has been expanding in terms of known objects ever since. There are currently over 2,000 catalogued Kuiper belt objects with well-determined orbits. The estimated total number of objects larger than 100 kilometers in diameter is thought to be in the hundreds of thousands. The total mass of the belt is estimated to be somewhere around 1/10 the mass of Earth, which sounds small until you consider that this is material spread across an enormous volume of space in individual bodies, none of which ever came together into something larger. Why didn't they? The leading explanation involves Neptune. As the outer solar system evolved, Neptune's gravity continuously disrupted the outer belt, preventing material from accumulating into a planet-sized body. The belt we see now is not a failed planet. It is a region where planet formation was interrupted before it could finish. The scale of all of this, from the Sun outward to the belt's outer edge, is not something that resolves easily into a felt sense of distance. Light, travelling at roughly 300,000 kilometers per second, takes about 8 minutes to reach Earth from the Sun. To reach the inner edge of the Kuiper belt, that same light takes approximately 4 hours. To reach the outer edge, somewhere between 5 and 7 hours depending on where the edge is drawn. A spacecraft travelling at speeds achievable with current technology takes not hours but decades to cross that distance. New Horizons, launched in 2006, reached Pluto in 2015. 9 years, and Pluto is at the inner edge of the belt. The solar system, in other words, is not the compact arrangement it sometimes appears to be in diagrams. The belt alone occupies more volume than everything inside Neptune's orbit combined, and it is still largely unobserved. Most of what is out there has never been looked at directly. The objects we know about are the ones bright enough or close enough in their orbits at the right moment to have appeared in survey data. The rest drift in orbits that take hundreds of years to complete, in temperatures that hover near absolute zero, in darkness that is not quite absolute. The Sun is still visible from there, still a source of light, just not enough to warm anything. The second skin of the solar system, if that is a way to think about it, and it might not be the right frame exactly, sits out there regardless. Whether any mind is currently considering it or not, it continues. The objects at those distances are not all the same. Some of them move in ways that fit neatly into known patterns. Others behave as if something is nudging them, something that hasn't been found yet. There is ice on your planet that is older than anything alive. Locked inside Antarctic cores, compressed under kilometers of accumulated snowfall, are layers of atmosphere from before recorded history, air bubbles from centuries past, trapped and preserved in crystalline water that has not seen sunlight since it fell. Scientists extract these cores and read them like text. They find the chemical signatures of ancient winters, volcanic eruptions, shifts in atmospheric composition that predate every civilization that ever named a star. That ice is old, but the ice in the Kuiper belt is older by an order of magnitude that makes the comparison almost useless. Come closer for a moment, not to the belt, to the idea of what freezing means at that distance. In the early solar system, the region beyond what would eventually become Neptune was cold in a way that is difficult to situate. Temperatures out there during those first millions of years hovered somewhere between 20 and 30 Kelvin. To put that in terms that mean something, water freezes at 273 Kelvin. The temperature at which most gases we think of as permanent, nitrogen, carbon monoxide, methane, freeze into solid form sits between 20 and 90 Kelvin depending on the compound. At 20 to 30 Kelvin, almost everything freezes, not gradually, quickly. The gas cloud that surrounded the young sun in its outer regions was transitioning from vapor to solid in timescales that were, by geological standards, nearly instantaneous. What formed out there was not pure water ice, it was a mixture. Water, yes, but also methane ice, carbon monoxide, ammonia, complex carbon-bearing molecules that form when simple chemistry, hydrogen, carbon, nitrogen, oxygen, is exposed to ultraviolet radiation and low temperatures over long periods. These compounds are called tholins. They are not a specific molecule but a category, a family of reddish-brown organic material that forms in conditions that no longer exist in the inner solar system. They form slowly, they persist. The frozen bodies in the Kuiper belt are made of this mixture. Layers of it, accumulated during formation, modified slightly over the subsequent 4 billion years by cosmic radiation and occasional impacts, but fundamentally still carrying the chemical composition of the early outer solar system. Here is where it becomes worth slowing down. When we say a Kuiper belt object preserves the chemistry of the early solar system, we mean something specific. We do not mean it is a perfect record. Cosmic rays, high-energy particles travelling through interstellar space, penetrate the surfaces of these objects to depths of about a metre over billion-year timescales, altering organic molecules, darkening surfaces, driving off some volatile material. The outermost layer of any Kuiper belt object is not pristine. It has been processed, changed. But below that surface layer, the material is largely undisturbed. An object large enough, a few kilometres across say, has an interior that has not been exposed to radiation, not been warmed above 30 Kelvin, not been touched by anything since the solar system was young. The interior of a mid-sized Kuiper belt object is, in a real chemical sense, a sample of conditions from 4.5 billion years ago. This is why the study of comets matters beyond their visual drama. When a comet, which is most often a displaced Kuiper belt object, falls inward toward the sun, its surface heats for the first time. Volatile material sublimates. Gas and dust stream outward, forming the tail. And in that material, carried outward by sublimation, are compounds that formed in the outer solar system during its earliest period. The Rosetta mission, which orbited Comet 67P/Churyumov-Gerasimenko between 2014 and 2016, detected glycine in the comet's outgassing, an amino acid, one of the building blocks of proteins, present in a frozen body that formed beyond Neptune. That single detection altered, or at least deepened, a question that had been sitting quietly for decades. Where did the organic chemistry necessary for life on Earth come from? The answer is not simple, but comets, and by extension the Kuiper belt objects that become comets, are part of the conversation now in a way they weren't before. The self-correction arrives somewhere around here when thinking about what memory means in a physical system. Ice does not remember in any active sense. It does not store information the way a brain stores experience. What it does is preserve chemical state, molecular arrangements that were fixed at a particular moment under particular conditions and have not had enough energy input since to rearrange. The memory is passive. It is the memory of a fingerprint left in clay before the clay hardened. The fingerprint is still there not because the clay chose to keep it, but because nothing came along to erase it. The Kuiper belt has been cold enough and undisturbed enough for the fingerprint to remain. What was pressing into that clay 4.5 billion years ago was a solar system in the process of becoming itself. The sun was still contracting. The planets were still accumulating. The disk of gas and dust that surrounded the young sun, called the protoplanetary disk, was in the process of sorting itself out, heavy elements settling closer to the sun, lighter volatile compounds pushed outward by the radiation pressure and temperature gradients. The Kuiper belt sits at the far edge of where that sorting happened. The objects there are, in a sense, and it seems reasonable to think of it this way, the leftover material from the outer edge of that sorting process. Not failed planets, not debris, just the portion of the disk that was too far out, too cold and too sparse to coalesce into something larger. Time at these scales does something to the concept of change. 4 billion years sounds like a duration. It sounds like a long time during which things happen. And things did happen in the Kuiper belt. Neptune migrated outward, reshaping the belt's inner regions. Objects collided, broke apart, recombined. Some were flung outward into the scattered disk. Some fell inward and became comets. The belt is not static. But for any individual object sitting in a stable orbit, the change has been minimal. A body in the outer Kuiper belt, in a near-circular orbit, in the right resonance relationship with Neptune to avoid gravitational disturbance, that body has experienced approximately the same conditions for most of its existence. Cold, dark, irradiated slowly, barely touched. 4 billion years of barely touched. The surface has darkened. The outermost molecules have been reorganized by radiation. But the interior, the part that has never seen anything, is the same as it was when the solar system was young enough that there were no planets yet. There is a particular kind of quietness in that fact, not a dramatic quietness. Not the quietness of something waiting, just the quietness of a physical state that has had no reason to change and so hasn't. The ice in the Kuiper belt does not know it is old. It does not hold its history consciously. It simply is what it is, a chemical arrangement fixed at a specific moment in time, continuing to exist in the same form, because the conditions that would alter it have not been present. It seems, when sitting with that long enough, like the most complete kind of stillness there is, not chosen, not maintained, just persisting, because nothing has come along yet to interrupt it. The surfaces of these objects, though, are a different matter. The outermost layers have been altered, and the colour of that alteration, the specific reddish tint that radiation and organic chemistry produce over billion-year timescales, turns out to carry its own kind of information. That information is not all the same across the belt. Some objects are red, some are almost grey, the difference is not random. Pluto was discovered in 1930. For 76 years after that, it was a planet. The 9th one. Smaller than expected, stranger in orbit than the others, but a planet nonetheless, named, counted, included in diagrams that hung in classrooms and on the walls of children's bedrooms across the second half of the 20th century. Then in 2006, the International Astronomical Union voted. Pluto was reclassified, dwarf planet, no longer the 9th. The solar system officially had 8. The argument that followed was loud and lasted years. Some of it is still going. But the part of that story most worth considering is not what Pluto lost. It is what the reclassification revealed about the place Pluto actually occupies, and what surrounds it out there. Pluto is not alone. That sentence sounds simple. It is simple, but the implications of it take a moment to settle. When Pluto was discovered, the technology available could only detect objects of a certain brightness at that distance. Pluto, at roughly 2,300 kilometers in diameter, was just barely detectable. Anything smaller, which is to say almost everything else in the Kuiper belt, was invisible to the instruments of the time, so Pluto appeared singular, an oddity past Neptune, a planet that didn't quite fit but had nowhere else to be categorized. What the decades after 1992 revealed, as survey technology improved and wide-field sky surveys began systematically imaging the outer solar system, was that Pluto is not an oddity, it is a member. One of the larger members, but a member nonetheless, of a population of objects that share its region of space, its general composition, and in many cases its orbital characteristics. The Kuiper belt, once it became observable, recontextualized Pluto completely. Consider what that means for a moment. An object sits in its orbit for 67 years as the 9th planet. Textbooks are printed. Children memorize its name. It occupies a fixed position in the human understanding of the solar system. And then, not because Pluto changed, but because the region around it finally became visible, its category shifts. The universe did not reclassify Pluto. The universe never classified it in the first place. What changed was the resolution of the image, the detail, the ability to see what had always been there. And what had always been there was a belt full of objects. The population of Kuiper belt objects falls into several dynamical groups, and understanding those groups is the only way to understand where Pluto sits within the larger structure. The first group is called the classical Kuiper belt, sometimes referred to as the cold classical belt. These are objects in near circular orbits, relatively undisturbed, sitting between roughly 42 and 48 astronomical units from the Sun. The word cold here does not refer to temperature. Everything in the Kuiper belt is cold, but to orbital excitation. Low inclination, low eccentricity orbits. Stable. These objects are thought to have formed roughly where they are now, and to have remained there. Their surfaces tend to be red, consistent with long-term radiation processing of organic material without significant disturbance. The second group is called the resonant population. These are objects whose orbital periods are in precise mathematical relationships with Neptune's orbital period. Pluto belongs here. It completes 2 orbits for every 3 that Neptune completes, a 3-to-2 resonance, which places Pluto and the objects sharing its resonance in a class called Plutinos. There are hundreds of known Plutinos, possibly many thousands that haven't been detected yet. The third group is the scattered disk, objects with highly elliptical orbits, inclined at steep angles to the plane of the solar system, reaching far beyond the classical belt's outer edge. These are thought to have been gravitationally scattered by Neptune during its outward migration. Pluto, in this framework, is not anomalous. It is a large Plutino, a well-studied representative of a dynamical family that was simply invisible until telescopes became good enough to find the others. The central metaphor worth holding here, the only one this chapter needs, is the idea of a portrait becoming clearer, not changing, becoming clearer. The solar system was always the way it is. The Kuiper belt was always populated. Pluto was always a Plutino orbiting among hundreds of similar objects. None of that changed between 1930 and 2006. What changed was the resolution of the image humanity had of its own solar system. Each decade of improved telescope technology, each new sky survey, each spacecraft mission added detail to a picture that had always existed but could not previously be seen. The reclassification of Pluto was not a demotion. It was a focusing of the lens. And when the lens focused, what it revealed was not a lonely outlier past Neptune. It was a structured, populated region with dynamical families and chemical gradients and size distributions that follow predictable statistical patterns. Pluto within that region is among the largest, but it is not alone, and it never was. Eris, discovered in 2005, was initially thought to be larger than Pluto. Later measurements revised that estimate. Eris is now thought to be very slightly smaller than Pluto in diameter, though more massive. Make. Haumea, which has a ring system and 2 moons and rotates so fast it is visibly elongated. Quaoar, sitting in a near circular orbit beyond the classical belt's outer edge, with a ring of its own that sits at a distance where rings were not expected to be stable. Each of these objects was unknown before 1992. Each of them is now a named dwarf planet or dwarf planet candidate, with known orbital parameters, estimated sizes, and in some cases surface composition data from spectroscopic observation. Each of them shares the region that Pluto occupies. Pluto's moons, Charon, Nix, Hydra, Kerberos, Styx, were discovered between 1978 and 2012. Charon is large enough relative to Pluto that the two are sometimes described as a binary system, with both bodies orbiting a point in space that lies outside Pluto's surface. That configuration is not unique in the Kuiper belt. Binary systems are surprisingly common out there, formed in conditions that allow gentle gravitational capture rather than violent collision. When New Horizons reached Pluto in July 2015, the images it returned showed something no model had fully anticipated. A heart-shaped plain of nitrogen ice, mountain ranges of water ice rising 3,000 meters from the surface, a hazy atmosphere, thin but real, extending hundreds of kilometers above the surface. A varied terrain with regions of different ages, suggesting that Pluto's surface has been geologically active within the last 100 million years, recent by planetary standards. The object that had been a point of light for 85 years revealed itself as a world. Not the largest world, not the most dramatic, but a world with structure and history and a surface that had changed, that had done things, that bore the record of processes operating over long timescales. And somewhere in the outer Kuiper belt, past the region New Horizons traversed after Pluto, there are hundreds of thousands of objects that have never been photographed at resolution. Their surfaces are unknown. Whether they are geologically active, whether any of them are, is unknown. Whether any of them have atmospheres, however thin, is unknown. Pluto gave us one data point, a detailed one, but one. The question, and it is worth letting it sit without immediately reaching for an answer, is what the other large Kuiper belt objects look like up close. Eris, Make, Quaoar, Sedna. Objects with names and orbital data and estimated sizes, but no close imagery. No surface maps, no atmospheric measurements. They are, from our current vantage, what Pluto was in 1929, points of light with inferred properties and no direct observation. Whether any future mission reaches them, that is uncertain. The distances involved are severe. New Horizons took 9 years to reach Pluto. Sedna, at its closest approach to the Sun, is still more than 76 astronomical units away. A mission to Sedna at current propulsion technology would take decades, so they remain for now what they've always been, present, orbiting, unvisited. Pluto was never the outlier, it was just the first one close enough and large enough and bright enough to be seen. What lies at the outer edge of the belt, in orbits that reach far beyond anything Pluto traces, belongs to a different category entirely. Objects whose paths extend so far that calling them Kuiper belt objects requires some flexibility in the definition. You will never think about most of them. That is not a criticism, it is just true. There are objects in the Kuiper belt that have been logged in a catalogue with a designation, a string of numbers and letters assigned by the Minor Planet Center, and nothing else. No name, no follow-up observation, no spectroscopic analysis, no estimate of surface composition, a position, an orbit, a number. They exist in that state right now. While you are reading this, while you are lying still, while the room around you holds its particular nighttime quiet, those objects are out there, moving through their orbits, unthought of by any mind anywhere. That fact does not require a response. It is simply what is. There are roughly 3,000 Kuiper belt objects with well-characterized orbits in current databases. Well-characterized means observed across multiple nights, sometimes multiple years, enough times to calculate a reliable orbital path. Below that threshold, objects glimpsed once or twice, not enough to confirm an orbit, the number is larger. And below that, objects that haven't been detected at all, that are too small or too dark or currently in a part of their orbit that no survey has imaged recently. Number in the hundreds of thousands at minimum. Each one is a physical object. Each occupies space. Each has mass. Each follows the same gravitational mathematics that governs every other body in the solar system, from the Sun to the smallest grain of dust in the inner asteroid belt. The physics does not distinguish between the named and the unnamed. Gravity does not care whether an object has been observed. What does it feel like to have no claim on anyone's attention? You've probably felt something like it. A day when nothing you did registered. A moment in a crowd where your presence made no difference to the shape of the room. Not loneliness exactly, something quieter. The sensation of being present and unremarked upon simultaneously. The objects in the Kuiper belt do not feel this. That has to be said plainly. They have no experience of being observed or unobserved. There is no interior state to a frozen body drifting at 40 astronomical units. No waiting, no awareness of the attention that has or hasn't been directed toward it. But the parallel is still worth considering, not because it illuminates the objects, but because it might illuminate something about attention itself, about what it means for a mind to single out one thing from a field of many things and hold it. The objects we have named, Pluto, Eris, Makemake, Arakoth, we named because we could see them, because they were large enough or bright enough, or happened to cross a patch of sky we were already watching. The selection was ours. The significance was assigned by the act of looking. This is where the metaphor arrives, and it is a simple one. A dark room full of objects. You enter with a small light. The beam falls on one thing, a chair, a table, a book left face down. You see it clearly. You name what it is. The rest of the room is still there, filled with things that are exactly as real as what you're looking at. Your light does not create them. It does not affect them. It simply makes one of them, temporarily, the thing you know. The Kuiper belt is that room. Every telescope humanity has ever pointed at the outer solar system is that small beam of light. What the beam has found is remarkable. What it has not yet found is almost certainly more. The unnamed objects, the ones with designations only or no designation at all, are not lesser objects. The physics operating on them is identical to the physics operating on Pluto. Their interiors carry the same preserved chemistry of the early solar system. Their surfaces have been processed by the same cosmic radiation over the same timescales. If any of them are large enough, they may have undergone differentiation, heavier material sinking toward a core, lighter material rising toward a surface, the same internal process that shaped the terrestrial planets. Some of them may be binary systems, two bodies orbiting each other, travelling together through the belt, never observed closely enough to know. Some may have surface features as varied as Pluto's, plains, mountains, cracks where subsurface material expanded and fractured the crust. Some may have thin atmospheres in the warmest part of their orbits, sublimating briefly before refreezing as they move farther from the sun. We do not know. That is not a temporary condition that will resolve soon. The sheer number of objects combined with the distances involved and the limitations of current survey technology means that most Kuiper belt objects will remain uncharacterized for a very long time. There is a word that comes up in planetary science when discussing objects like these: primitive. It does not mean simple exactly. It means unprocessed, unchanged from the original conditions of formation. A primitive body is one that has not been significantly altered by heat, by geological activity, by the presence of liquid water, by collision with other large bodies. It retains the chemical and physical state it had when it formed. Most Kuiper belt objects are primitive in this sense. The outer solar system never got warm enough, never got dense enough with large bodies to drive the processes that rework material. What formed out there stayed more or less as it formed. This makes them scientifically valuable in a way that Earth, for instance, is not. Earth has been reworked so thoroughly, and by plate tectonics, by the water cycle, by billions of years of biological and chemical activity, that its original surface is essentially gone. The Kuiper belt objects still have theirs. The ones with no name carry that value whether or not any instrument has ever measured it. You will never think about most of them. That is still true. It was true at the beginning of this chapter, and it remains true now. The repetition is not accidental, just honest. The number is too large, the distances are too great. The technology to observe them individually does not yet exist and may not for generations. But they are not waiting. They are not accumulating some deficit of attention that will need to be addressed eventually. They are in their orbits. Moving at speeds that are slow by inner solar system standards, a Kuiper belt object at 45 astronomical units from the Sun moves at roughly 4 to 5 kilometers per second compared to Earth's 30, completing circuits of the Sun that take 200, 300, 400 years depending on the orbit. An object in a 400-year orbit has completed its circuit roughly 11 million times since the solar system formed. 11 million quiet loops, each one indistinguishable from the last, each one unremarked upon. It is possible that attention changes the thing observed. In quantum mechanics, at certain scales, observation has physical consequences. But at the scale of a Kuiper belt object that does not apply. The object is what it is regardless. The attention, or the absence of it, belongs entirely to the observer, and is the thing this chapter keeps returning to, and perhaps never fully resolves. Whether attention is something given, or something that simply lands, whether the unnamed objects are missing something by going unobserved, or whether that framing belongs entirely to the mind doing the observing. It seems sitting with it like the second option, but the question is worth leaving slightly open. The objects that do get observed, the ones that cross a survey field at the right moment, that appear as moving points in back-to-back images, sometimes reveal on closer inspection that they are not alone, that they travel in pairs. There is a kind of order in the solar system that does not announce itself. It does not appear in the broad strokes, the planets in their lanes, the sun at the centre, the general arrangement that diagrams have made familiar since childhood. It appears instead in the fine structure, in the ratios, in the quiet mathematical relationships between objects that never touch and never communicate except through the slow, patient intermediary of gravity. These relationships are not designed, they are not coordinated. They emerge over millions of years from a process that is entirely indifferent to its own outcomes, and yet the outcomes have a precision that, when you first encounter the numbers, can feel almost deliberate. Neptune completes one orbit of the Sun approximately every 165 years. Pluto completes one orbit every 248 years. Those two numbers do not seem at first glance to be in any particular relationship with each other, but if you divide 248 by the 165, you get something very close to 3/2. Pluto completes 2 orbits in almost exactly the time Neptune completes 3. The ratio holds not approximately, not loosely, but with a precision that has been stable for hundreds of millions of years and will remain stable for hundreds of millions more. This is what an orbital resonance looks like from the outside. 2 periods, a simple ratio, and underneath that ratio, a gravitational architecture of considerable depth. The mechanism is worth following slowly because it is not obvious that a simple ratio should be stable, and the reason it is stable is the most interesting part. Imagine Neptune moving along its orbit, completing its slow circuit of the Sun every 165 years, and imagine Pluto moving in its own orbit, more elliptical, more inclined relative to the plane of the solar system, reaching farther from the Sun at its most distant point and coming closer than Neptune at its nearest. These two orbits cross. Pluto's path at certain points in its circuit passes through the region of space that Neptune also occupies on its own orbit. This sounds like a collision waiting to happen. It is not. And the reason it is not is the resonance itself. Because Pluto completes exactly 2 orbits for every 3 Neptune completes, the positions of Neptune and Pluto at any given moment are not random relative to each other. They are correlated. Every time Pluto passes through the region of its orbit that crosses Neptune's path, Neptune is somewhere else, not nearby, but on the opposite side of its own orbit, or far enough away that the gravitational interaction is minimal. The geometry of the resonance arranges their encounters so that close approaches are systematically avoided. Pluto has been crossing Neptune's orbital path for billions of years without coming anywhere near a dangerous proximity to Neptune, because the timing is always off in exactly the right way. The gravitational nudges that Neptune does exert on Pluto, small occurring repeatedly at the same orbital phases, do not push Pluto out of the resonance, they reinforce it. A body that drifts slightly out of the 3:2 ratio receives gravitational corrections from Neptune that push it back. The resonance is self-stabilizing. Objects that find themselves in it tend to stay. This is where confidence has to become slightly more careful because the word tend carries weight here that should not be ignored. Most objects in Neptune's 3:2 resonance are stable over the age of the solar system. Numerical simulations running the orbital dynamics forward for billions of years show the Plutino population largely intact, but some fraction of Plutinos, depending on their exact orbital parameters within the resonance, are only metastable, stable for hundreds of millions of years, but eventually susceptible to being scattered outward into the scattered disk or inward toward the inner solar system. The resonance is robust, but it is not perfectly sealed. It seems, and it is worth keeping the word seems, that most Plutinos are genuinely long-term stable, but the boundary between stable and metastable is not always easy to determine from current observational data. What is certain is that 3:2 resonance with Neptune is the most populated dynamical niche in the Kuiper belt. Hundreds of known objects share Pluto's resonance. The population of undiscovered Plutinos is likely much larger, and the 3:2 is not the only resonance Neptune maintains. There are objects in a 2:1 resonance, one orbit for every 2 of Neptune's, and in a 5:3 resonance, and in several others. Each resonance represents a stable orbital niche, a region of orbital parameter space where Neptune's gravity, rather than disrupting, protects. Between these resonances are regions where Neptune's influence is destabilizing, where objects that stray into those zones are gradually perturbed into more chaotic orbits and eventually removed from the belt entirely. The belt, seen this way, is not a uniform cloud of objects spread continuously across a range of distances. It is structured, populated in specific zones and depleted in the spaces between them. The resonances are occupied. The regions between resonances, called the chaotic zones, are not. This structure was not placed deliberately. It grew from the interaction of Neptune's gravity with whatever population of objects existed in the outer solar system following the planet's formation and migration. And Neptune did migrate. This is now well established in planetary science, supported by multiple independent lines of evidence, including the orbital structure of the Kuiper belt itself. In the early solar system, Neptune formed closer to the Sun than it currently sits, probably in the range of 20 to 25 astronomical units, compared to its current 30 astronomical units. Over the first few 100 million years of the solar system's history, gravitational interactions with the planetesimal disk, the vast cloud of small icy and rocky bodies that surrounded the young outer planets, caused Neptune to migrate outward. As it moved, it swept its resonances outward with it, capturing objects into those resonances as it went, and scattering others into the scattered disk or out of the solar system entirely. The current structure of the Kuiper belt, its resonant populations, its classical component, its outer edge, is largely a record of Neptune's migration. The belt did not form in its current configuration. It was shaped into its current configuration by a planet moving through it over millions of years, leaving its gravitational fingerprint in the distribution of everything it passed. There is something worth pausing at here, even if it resists being stated too cleanly. The order that exists in the belt, the resonances, the stable niches, the mathematical ratios between orbital periods, emerge from a process that involved no planning, no optimization, no preference for one outcome over another. Neptune migrated because it was losing angular momentum to the planetesimal disk through repeated gravitational interactions. Objects were captured into resonances because their orbital periods happened to be near the right ratio when Neptune's resonance swept through their location. The ones that were captured stayed. The ones that were not mostly did not. What remains is the subset of initial conditions that survived. The resonances look precise because imprecise versions were gradually removed. The 3:2 resonance looks stable because objects in unstable versions of it are no longer there. The solar system is, in a sense that runs all the way through its structure, a record of what has persisted, and persistence out there is determined by the mathematics that operates without awareness of what it is doing. It is tempting to call this elegant. It might be, but it is also worth noticing that elegant is a word that belongs to the observer, not to the process. The process does not know it is elegant. It does not know anything. It simply continues, the same today as it was 4 billion years ago, the ratios holding, the resonances maintaining themselves, Neptune and Pluto tracing their separate paths in a coordination that nobody arranged, and nothing will disrupt for a very long time. Beyond the resonant populations, past the outer edge, Where Neptune's stabilizing influence fades and the classical belt gives way to something less structured, the orbits begin to look different, more elongated, more inclined, as if something other than Neptune has been at work. The classical Kuiper belt has edges, an inner one, around 42 astronomical units from the Sun, where the influence of Neptune's resonances begins to thin, and an outer one, somewhere near 48 astronomical units, where the density of objects drops sharply, more sharply than any model predicted before it was observed. This outer edge is real. It shows up in survey data consistently. Objects beyond it are not absent, but they are rare, and they move differently. Their orbits are not the near circular low-inclination paths of the classical belt. They are stretched, tilted. Some of them reach distances that dwarf anything in the classical population. This region past the classical belt's outer edge is where the solar system begins to feel less like a system and more like an open question. The scattered disk is not a belt in the way the Kuiper belt is a belt. It does not occupy a bounded ring of space at a consistent distance from the Sun. It is a population of objects with highly eccentric orbits, orbits so elongated that a single object might spend most of its time beyond 100 astronomical units from the Sun, then swing inward past Neptune before retreating again. The time spent close to the Sun is brief. The time spent in the outer reaches is not. An object in a scattered disk orbit with a perihelion, its closest approach to the Sun, near 30 astronomical units, and an aphelion, its farthest point, near 300 astronomical units, spends the overwhelming majority of its orbital period in the outer portion of that path. Not because anything is holding it there, but because orbital mechanics assign more time to the slower-moving distant arc of an ellipse than to the fast-moving inner arc. The object accelerates as it falls toward the Sun, passes through the inner portion of its orbit quickly, then decelerates as it climbs outward again. The cold of the outer arc is not meaningfully different from the cold of the inner arc because both are cold in a way that temperature as a live concept cannot accommodate. At 100 astronomical units from the Sun, the solar flux, the amount of energy arriving from the Sun per unit area, is 10,000 times weaker than at Earth's distance. The Sun is still there. It is still the brightest object in the sky by a significant margin, but it provides almost no warmth. Surfaces at that distance sit at temperatures near 10 to 20 Kelvin, depending on the object's reflectivity and the exact distance. 10 Kelvin, that is approximately minus 263 degrees Celsius, 3 degrees above absolute zero. At that temperature, molecular motion is not absent. Absolute zero, the point at which it would theoretically cease, is unreachable in practice, but it is reduced to a minimum. Atoms in a crystal lattice vibrate with the smallest possible amplitude the laws of thermodynamics allow at that energy state. Chemical reactions that would proceed readily at room temperature do not proceed at all. The surface of a scattered disk object at aphelion is as close to motionless at the molecular level as matter in the natural universe gets. There is a comparison that almost forms here, between that molecular stillness and some other kind of stillness that might feel familiar. But it does not quite hold, because the stillness out there is not the stillness of rest or of waiting. It is the stillness of an energy state so low that the usual categories of active and inactive stop applying cleanly. Better, perhaps, to just leave it as what it is, matter at 10 Kelvin in darkness, at 100 astronomical units from the nearest star, following a path that will eventually bring it inward again in a few thousand years. The scattered disk objects are thought to have originated in the region where the classical Kuiper belt now sits, or closer in the trans-Neptunian region that existed before Neptune's migration reshaped everything. As Neptune moved outward, its gravitational influence scattered some objects outward rather than capturing them into resonances. These scattered objects received energy kicks that pushed their orbits into highly elliptical shapes, sending their aphelia far into the outer solar system while keeping their perihelia near Neptune's current orbit. Eris is the largest known scattered disk object. It has an orbital period of approximately 559 years and an aphelion near 97 astronomical units. Its surface is one of the most reflective in the solar system, covered in fresh methane ice that may have condensed as the object moved inward, and its previous surface ice is sublimated and then refroze. Eris has one moon, Dysnomia, which orbits it with a period of about 16 days. The high reflectivity of Eris is itself a kind of record. It suggests that Eris has been in its current orbit long enough for its surface chemistry to have cycled, warming slightly near perihelion, losing some volatile material, then refreezing that material as it retreats. The white surface is recent in astronomical terms. What the surface looked like before the most recent infall cycle is unknown. Past the scattered disk, past even the most eccentric scattered disk orbits, there is a region that sits uncomfortably between categories. Sedna was discovered in 2004. Its perihelion is approximately 76 astronomical units, well outside Neptune's gravitational reach. Its aphelion is somewhere near 937 astronomical units. Its orbital period is estimated at approximately 11,000 years. These numbers placed it immediately outside any existing classification. It is too far from Neptune at perihelion to have been scattered by Neptune. It is not far enough or in the right orientation to be confidently classified as an inner Oort cloud object. It occupies a region, the inner reaches of what some researchers call the extended scattered disk, or the detached population, that does not have clean edges or a settled name. A second object, 2012 VP113, was found in 2014 with similar characteristics. A perihelion well beyond Neptune, an orbit that reaches hundreds of astronomical units from the Sun. No clear mechanism to explain how either object got where it is. Both objects, and several others discovered since, have perihelia that cluster in a way that seems, without yet being established, non-random. Their orbits share orientations that are unlikely to be coincidental if the only forces acting on them are the known planets. This clustering is what led to the hypothesis of a distant, massive, undetected body influencing the outer solar system. The hypothesis remains unconfirmed. The clustering remains unexplained. The outer edge of the scattered disk is not a line. It is a gradient, a thinning, a region where the density of objects decreases, not because something stops them, but because the conditions that would have placed objects there in the first place become rarer and rarer with distance. And yet objects are found farther out each decade as survey sensitivity improves. Sedna was a surprise in 2004. The objects that will be discovered in the next 20 years of outer solar system surveys are unknown. The instruments coming online, the Vera C. Rubin Observatory in Chile, which will conduct a 10-year legacy survey of space and time beginning observations in the mid-2020s, will increase the known population of trans-Neptunian objects by an order of magnitude or more. Many of those objects will be in orbits that extend far past anything currently catalogued. What that will reveal about the structure of the outer solar system, whether it will clarify the clustering, confirm or rule out the distant planet hypothesis, or simply add complexity, cannot be predicted from here. The outer solar system is answering questions at a rate slower than it is generating them. That may not change soon. It seems, in fact, like a condition that has characterized the study of that region since the first objects were found beyond Neptune, each discovery expanding the space of what is unknown faster than it contracts it. The question this chapter began with, what lies past the classical belt, does not have a closed answer. The scattered disk, the detached population, Sedna and its companions in orbits that reach near 1,000 astronomical units. And past all of that, something that is not quite the Kuiper belt and not quite interstellar space, where the sun's gravity still holds but only barely, and the objects that exist there have not been counted and may not be for a long time. Farther than that is not a direction, it is a condition. When a Kuiper belt object is pulled inward, scattered by Neptune, nudged by a resonance, set on a path toward the inner solar system, what it was before that journey is visible only briefly in the material it releases as it warms. Following that journey backward, from the bright object that crosses Earth's sky to the quiet frozen body it used to be, is a reversal. The next chapter traces slowly. A comet arriving in the inner solar system is already dying, not dramatically, not all at once, but the process that makes a comet visible, the sublimation of surface ices, the release of gas and dust, the formation of the coma and tail that make it bright enough to see, is the same process that is consuming it. Every pass close to the sun removes material. The comet that lights up the sky is losing itself to the visibility. What it was before that, before the first warming, before the first sublimation, is a different thing entirely. Quieter, colder, unremarkable in almost every way that matters for detection. The nucleus of a comet, before it enters the inner solar system for the first time, is an object indistinguishable from any other mid-sized Kuiper belt body. A few kilometers across, perhaps, irregular in shape, not the smooth sphere that gravity produces in larger bodies, but something lumpy, asymmetric, shaped by the accidents of accretion rather than by any organizing force. Its surface is dark, darker than coal in many cases. The albedo, the fraction of incoming light that a surface reflects, of a typical cometary nucleus is between 2 and 6%. It absorbs almost everything that hits it and reflects almost nothing. At 40 astronomical units from the sun, reflecting 2 to 4% of already faint sunlight, such an object is effectively invisible without dedicated survey instruments. It sits in its orbit, completing slow circuits over hundreds of years, accumulating nothing, losing nothing, waiting, though waiting is not the right word because waiting implies anticipation of something, and there is nothing anticipatory about a frozen body in the outer solar system. It simply continues. What begins the inward journey is almost always a gravitational perturbation. Something shifts the orbit. Neptune most commonly, a close enough approach to change the orbital parameters, to reduce the perihelion, to set the object on a path that brings it closer to the sun on each subsequent pass. Or an interaction with another Kuiper belt object. Or in some cases, the slow cumulative effect of a gravitational resonance becoming unstable, releasing the object from its stable niche into a more chaotic trajectory. The change is not violent. From the perspective of the object, if perspective were a concept that applied, the gravitational perturbation would be imperceptible as an event. There is no moment of sudden acceleration, no detectable shock. The orbit simply changes, incrementally, over multiple passes, until the trajectory that was stable becomes one that reaches inward. The journey inward takes time. A Kuiper belt object shifted onto a path that eventually brings it to the inner solar system may take tens of thousands of years to arrive. During that time it remains frozen and dark and undetectable. The trajectory is changing. The destination is approaching, in the slowest possible sense of the word. Nothing on the surface of the object reflects any of this. It looks the same at 35 astronomical units as it did at 42. The change begins around 5 astronomical units from the Sun, Jupiter's orbit. Not because Jupiter does anything at that point. The threshold is thermal, not gravitational. At 5 astronomical units, the solar flux is strong enough to begin warming the outermost surface layers of the nucleus. Not to temperatures that feel warm by any human standard. The surface might reach 150 Kelvin, still far below the freezing point of water, but warm enough for certain highly volatile ices to begin sublimating. Carbon monoxide sublimates at around 25 Kelvin, carbon dioxide at around 80 Kelvin. Water ice requires approximately 150 to 200 Kelvin, depending on its crystalline structure. So the first activity begins with the most volatile species, carbon monoxide and carbon dioxide lifting off the surface, carrying dust particles with them, beginning to form the tenuous coma that will eventually become visible. This is a process the object has, in all likelihood, never undergone before. If it is a dynamically new comet, one making its first pass through the inner solar system after a long residence in the Kuiper belt or Oort cloud, then the volatiles on and near its surface have been frozen since the solar system formed. The first warming is genuinely the first. The gas lifting off the surface is gas that has been locked in ice for 4.5 billion years. It is worth sitting with that for a moment. The release of gas from a cometary nucleus on its first perihelion passage is not just a physical process. It is the opening of something that has been sealed for the entire age of the solar system, and what comes out carries chemical information from that age. The molecular composition of cometary outgassing has been studied in detail for several comets, and the picture is complex. Water dominates, as expected. Comets are sometimes described as dirty snowballs, though the ratio of rock to ice in many cases is high enough that the inverse snowy dirt balls has been proposed as more accurate, and it is a distinction that matters when thinking about how the internal structure is organized. Beyond water, carbon monoxide, carbon dioxide, methane, ammonia, formaldehyde, methanol, hydrogen cyanide, and more complex molecules, glycine as mentioned when discussing the Rosetta mission's findings at 67P phosphorus, oxygen in molecular form. The nucleus of a comet before its first approach to the Sun contains all of this, frozen, preserved, sitting in a configuration that formed during the first few million years of the solar system's existence and has not been disturbed since. The Rosetta mission spent 2 years orbiting Comet 67P/Churyumov-Gerasimenko. It watched the comet become active as it fell toward perihelion in 2015. It mapped the surface, it measured the outgassing, it deployed a lander, Philae, which bounced twice on the surface before settling in a shadowed region where its solar panels could not charge. What Rosetta found was a comet with 2 distinct lobes, connected by a narrow neck, a contact binary, 2 objects that had come together gently at some point in the past and bonded. The surface was varied, smooth regions of fine-grained material, rough regions of consolidated ice and rock, active pits from which gas was visibly streaming during the approach to perihelion. The activity was not uniform. Some regions of the surface were far more active than others, based on composition and the angle of incoming solar radiation. 67P is not a first-time visitor. It has made multiple passes through the inner solar system, and its volatile content has been reduced with each one. What Rosetta measured was not the pristine chemistry of a Kuiper belt object at its first perihelion, but the altered surface of an object that has already given up some of its original material. The pristine version, the object as it was before any perihelion passage, is not directly observable. It exists in the interior, sealed beneath the processed outer layers, and the only way to access it would be to sample deeply enough to reach material that has never been warmed. The question of what a comet actually is, before it becomes a comet, sits somewhere between a classification problem and a genuinely physical one. Is a Kuiper belt object in a stable orbit a comet? The answer depends on definition. By composition, yes. It contains the volatiles that will eventually produce cometary activity if the orbit changes. By behavior, no. It shows no activity, no coma, no tail. The object does not become a comet at a specific moment. It becomes one gradually over the long inward journey, as activity begins at different volatile thresholds at different distances from the Sun. The Kuiper belt object and the comet are the same body at different points in its trajectory. The comet is what the Kuiper belt object becomes when it is seen. The Kuiper belt object is what the comet was when nobody was looking, and for most of its existence nobody was. What happens after the comet has made enough passes to exhaust its volatiles is less certain. Some cometary nuclei fragment completely. Some develop thick insulating crusts that suppress further activity, leaving a dark, inert body that continues in its orbit as an asteroid-like object. The endpoint of the cometary process is, in some cases, not easily determined from what is currently observable. The material a comet releases, the dust and gas streaming outward as it falls toward the Sun, does not travel with it. It spreads. Some of it intersects Earth's orbit at predictable points each year. The streaks that appear in a clear night sky on specific dates in August, in November and December, those are not random. They are the remnants of specific comets, and the paths they follow are older than the observation of them. The outer edge of the classical Kuiper belt ends more abruptly than it should. That sentence carries more weight than it might initially seem to. In planetary science, when something ends more abruptly than models predict, it is not an aesthetic complaint. It is a data point, a signal that something happened, something that the current understanding of how the solar system formed does not fully account for, and that whatever happened left a mark precise enough to be measured. The mark in this case is a drop in the number of observed Kuiper belt objects beyond approximately 48 astronomical units. Not a gradual fade, a relatively sharp boundary beyond which the cold classical population essentially ends. Why should that be surprising? In the early solar system, the disk of material surrounding the young Sun extended continuously outward. There was no reason in the initial conditions for the outer belt to end sharply at 48 astronomical units, rather than thinning gradually over a much larger range. The disk should have faded slowly, and if objects had simply formed and stayed where they formed, the Kuiper belt should be a much broader, more diffuse structure than it is. It is not. The outer edge is real, and it is sharp, and its sharpness requires an explanation. The explanation most consistent with current evidence involves Neptune. Not Neptune as it sits now in its near-circular orbit at 30 astronomical units, but Neptune in motion, Neptune during the period of planetary migration that reshaped the outer solar system in the first few 100 million years after the planets formed. The leading theoretical framework is called the NICE model, developed in the mid-2000s and refined significantly since. In this framework, the giant planets Jupiter, Saturn, Uranus, Neptune formed in a more compact configuration than they currently occupy. They were surrounded by a vast disk of planetesimals, small bodies containing in total far more mass than the current Kuiper belt holds. The gravitational interaction between the planets and this disk caused the planets to migrate, Jupiter moving slightly inward, Saturn, Uranus and Neptune moving outward. Neptune's outward migration was the most consequential for the Kuiper belt. As Neptune moved, it swept through the primordial outer disk, capturing some objects into resonances, scattering others onto eccentric orbits, and ejecting still others from the solar system entirely. the mass of the outer disk was dramatically reduced, by a factor of somewhere between 10 and 1,000 depending on the specific model, and the structure that remained was the Kuiper belt as it exists today. The outer edge at 48 astronomical units in this framework marks roughly the point where Neptune's migration stopped. Neptune reached its current orbit and ceased moving outward, leaving the region beyond it largely cleared of the material that once existed there. Objects that were at 48 astronomical units or farther when Neptune stopped migrating were either scattered or left in dynamically excited orbits, while the cold classical population that survived was the material that happened to be in the right place at the right time, near enough to be captured into stable resonances or left in near-circular orbits, far enough not to be ejected. No, perhaps that's not quite it. The picture is more nuanced than Neptune simply stopping and leaving a clean edge. The edge reflects a combination of Neptune's final position, the dynamics of resonance sweeping, and the original distribution of material in the primordial disk. The sharpness of the edge is real, but it emerged from a process with multiple contributing factors, not a single clean mechanism. What the edge tells us, regardless of the precise mechanism, is that Neptune moved. The structure of the Kuiper belt is evidence of planetary migration that happened 4 billion years ago and cannot be directly observed. The belt is the record. Here is where the metaphor arrives, and it is a quiet one. Imagine a beach after a wave has passed. The wave has moved up the sand, disturbed everything in its path, carried some material back with it as it retreated, and left a visible line, a boundary between the wet, disturbed sand and the dry sand that the wave did not reach. The line is sharp. It does not gradually fade from wet to dry over many meters. It marks the extent of the wave's reach with a precision the wave itself had no intention of creating. Neptune's migration through the primordial outer disk left a line like that. Not in sand, but in the distribution of objects across billions of kilometers of space. The wet sand, the disturbed, rearranged population, is the classical Kuiper belt. The resonant populations, the scattered disk. The line is the outer edge at 48 astronomical units. The dry sand beyond it is a region that Neptune's wave never reached, not empty but sparsely populated, containing only the objects that formed there and were never swept inward. The wave metaphor is imprecise in various ways. Neptune's migration was not a wave in any physical sense, and the analogy breaks down under pressure. But the image of a boundary created by the reach of a moving force captures something true about what the outer edge represents. Beyond 48 astronomical units, objects do exist. They are not common, and their orbits are not the near-circular, low-inclination paths of the cold classical belt. Some of them are in distant resonances with Neptune, the 1:2 resonance, for instance, which places objects at approximately 48 astronomical units, right at the outer edge, completing one orbit for every 2 of Neptune's. Others are in orbits that are dynamically detached from Neptune, high enough in perihelion that Neptune's gravity cannot significantly perturb them on any short timescale. These outer objects are studied with difficulty. Their distances make them faint. Their orbital periods, sometimes hundreds of years, mean that multiple decades of observation are required to fully characterize a single orbit. The Vera C. Rubin Observatory will find more of them when its survey begins, but characterizing what it finds will take time. Is that really what's happening at the outer edge? A simple record of where Neptune stopped? Or is there additional structure being missed by current surveys? The question is open. Some researchers argue that the outer solar system contains significant populations of objects that current surveys have not reached. Others suggest the outer edge is as sharp as it appears and the region beyond it is genuinely sparse. The data is not yet sufficient to settle the question. What the gap represents, underneath all the orbital mechanics and migration models, is time made visible. The early solar system was dynamic in ways that the current solar system is not. Planets were moving, mass was being redistributed. The architecture that now looks stable and settled was being actively constructed through processes that no longer operate at the same scale. The Kuiper belt is one of the few places where the results of that early dynamism are still readable, where the distances between things, the sharp edges and populated resonances, carry information about events that happened before Earth had a solid surface. The gap past 48 astronomical units was not always a gap. It was cleared by a planet moving outward through material that had been sitting there since the disk formed, sweeping and scattering and leaving a boundary where its influence ended. That boundary is still there. It has not closed. Nothing has filled it in the 4 billion years since Neptune stopped moving. The cleared region remains cleared, and the sharp outer edge of the classical belt remains sharp, a line drawn by planetary migration across billions of kilometers of space. The Kuiper belt ends. And then, past where it ends, objects still exist, scattered, detached, sitting in orbits that raise their own questions. But some of what lies beyond the classical belt is not scattered at all. Some of it is paired, two bodies travelling together through the outer solar system, maintaining their proximity across timescales that make the concept of companionship feel almost physical. Those binary systems, their existence, their formation, and what their prevalence tells us about conditions in the early outer solar system are what the next chapter turns toward. Two objects, orbiting each other, neither one the centre. That is the simplest description of a binary system in the Kuiper belt, and it is accurate as far as it goes, but it leaves out the part that is actually interesting, which is not the configuration itself, but what the configuration implies about the conditions under which it formed, and what it means for two bodies to have maintained that relationship across 4 billion years of otherwise undisturbed time. The Kuiper belt has an unusually high fraction of binary systems compared to other populations of small bodies in the solar system. Among the cold classical Kuiper belt objects, the ones in near circular low-inclination orbits thought to have formed roughly where they now reside, the binary fraction may be as high as 30%, possibly higher, given that close or faint binaries are difficult to detect and current surveys are almost certainly undercounting them. 1 in 3 cold classical Kuiper belt objects may be travelling through its orbit accompanied by another body, the two of them locked in mutual gravitational embrace, going nowhere in particular together. How they formed is the question that took the longest to answer, and the answer, when it came, required a different way of thinking about how small bodies interact in the outer solar system. The obvious mechanism, two objects colliding and the result being a binary, does not work well for the cold classical population. Collisions in the early outer solar system were possible, but the low relative velocities in that region mean that a direct collision between two similar-sized bodies would more likely result in merging than in the creation of a stable orbiting pair. A violent collision at higher velocities could produce debris that might coalesce into a satellite, but the binaries observed in the cold classical belt are often near equal in mass, the two components similar in size, which is not what violent collisions tend to produce. The mechanism that better fits the observations is called gravitational capture through dynamical friction, and later refined into a process called the streaming instability and subsequent pebble cloud collapse. In the early outer solar system, the density of small particles was locally high enough in certain regions for gravitational instabilities to develop within swarms of pebbles. These swarms would collapse under their own gravity, but instead of collapsing to a single body, two concentrations could form within the collapsing cloud and begin orbiting each other as they contracted. The binary would form not from a collision, but from a shared gravitational collapse, two bodies condensing out of the same cloud, already in orbit around their common centre of mass before either had fully consolidated. The central image this chapter holds, the only one it needs, is of two stones dropped simultaneously into still water very close together. Each produces its own ripples, but the ripples interact from the beginning, and the two disturbances are never fully independent of each other. The stones do not collide, they fall separately, and the medium around them registers both at once, and what forms is a pattern that neither stone produces alone. The binary Kuiper belt objects formed something like this, not from impact, from proximity in a collapsing medium. Two gravitational centres emerging together from the same material, already coupled before they were fully formed. What this implies for the cold classical belt is significant. The formation mechanism for equal mass binaries is gentle. It requires low relative velocities, sufficient local density of material, and conditions stable enough for the collapse to proceed without disruption. These conditions existed in the early outer solar system, but they are sensitive. If Neptune had migrated through that region before the binaries formed, the disruption would have prevented the gentle collapse from completing. The high binary fraction of the cold classical belt is therefore evidence, independent of the orbital structure evidence discussed earlier, that the cold classical objects formed in place before Neptune's migration disturbed the inner Kuiper belt regions. The binaries are, in this sense, a record of undisturbed formation. Their existence in that proportion, in that specific dynamical population, tells us something about timing. The outer belt was left alone long enough for these systems to form. The inner belt was not. The dynamics of a Kuiper belt binary are slow by any measure applicable to the inner solar system. Arakoth, the contact binary visited by New Horizons in January 2019, is the clearest example of where a binary eventually leads given enough time and gentle enough conditions. Its two lobes, named Ultima and Thule, are thought to have been a binary pair that slowly spiraled together over millions of years, their mutual orbit decaying through a process called Kozai-Lidov cycling, combined with tidal forces, until they came into contact and merged. The merger was gentle. The two lobes pressed together at low velocity, and the result is the shape New Horizons photographed. Two rounded forms joined at a narrow neck, like two spheres of different sizes touching at a single point. Arakoth's shape is direct evidence of the gentle formation and evolution conditions in the cold classical belt. A violent history would have produced a different shape, more irregular, more fractured, lacking the soothed lobes. The smoothness is a signature of slow processes operating over long timescales in an environment with low collision rates and low relative velocities. Other binaries in the Kuiper belt have not yet merged. They continue in their mutual orbits, separated by distances that range from a few hundred to tens of thousands of kilometers, completing their orbits around their common center of mass over periods of days to years depending on the separation and the masses involved. From a distance, from any distance at which they are currently observable, most of these binaries appear as single points of light. The angular separation between the two components is too small for current telescopes to resolve in most cases. Their binary nature is inferred from the way the combined light varies as one body passes in front of or behind the other, or from high-resolution imaging with space-based telescopes like Hubble, which has resolved a number of Kuiper belt binaries directly. The ones that Hubble has resolved show a range of configurations. Some are nearly equal in brightness, suggesting similar sizes. Some have a large primary and a much smaller secondary. Some have separations large enough that the mutual orbit takes years to complete, while others are close enough that a single orbit takes only a few days. The variety suggests that the formation process, while generally gentle, produces a range of outcomes depending on the specific conditions within each collapsing pebble cloud. 4 billion years is a long time for two objects to maintain an orbit around each other. Over that time scale, various processes act to evolve binary orbits. Tidal interactions between the two bodies transfer angular momentum and can either tighten or widen the orbit depending on the geometry. The Kozai lead-off mechanism, a gravitational influence from the distant Sun, can cause the inclination of the mutual orbit to oscillate, periodically raising the eccentricity of the orbit and bringing the two bodies closer at closest approach. Collisions with small impactors can perturb the orbit. Radiation forces, though weak at Kuiper belt distances, operate continuously and over billion-year timescales can produce measurable effects. The binaries that have survived to the present day are the ones whose orbits were stable against all of these perturbations. Some fraction of the original binary population has certainly merged, like Arakoth, or been disrupted. What remains is the subset that has maintained its configuration through 4 billion years of slow evolution. It seems, and this is the kind of observation that resists being stated too firmly, that stability in the outer solar system is less a condition that is achieved and more one that is continuously maintained, incrementally, against perturbations that never fully stop. The binaries that exist now exist because nothing has yet been large enough or close enough or persistent enough to end what began when two clouds of pebbles collapsed together in the early outer solar system. The two bodies travel together, neither leading, neither following, both orbiting the point between them that their combined gravity defines. That point moves through the belt at the same speed their common centre of mass moves, which is to say, slowly in a near circular path, completing a circuit of the Sun every few hundred years. 4 billion years of that. Approximately 10 million circuits, give or take depending on the specific orbit. 10 million quiet loops around a sun that was younger when they started than it is now. They are still out there, most of them unobserved, going nowhere in particular together. The surfaces of these objects, binary and single alike, carry colours that vary across the cold classical belt in ways that are not random. The redness of certain populations, the greyness of others, reflects something about formation, location and radiation history that the next chapter moves slowly through. Light arrives at the Kuiper belt diminished. At 40 astronomical units from the Sun, the intensity of sunlight is 1,600 times weaker than it is at Earth's distance. Not dim in the way a cloudy afternoon is dim in a way that requires numbers to appreciate. The Sun from that distance is still the brightest object in the sky by a large margin, but it provides almost no warmth and very little photochemical energy. A solar panel that generates a kilowatt at Earth's distance would generate less than a watt at 40 astronomical units. And yet that faint light, arriving continuously over billions of years, has done something to the surfaces of Kuiper belt objects. Something measurable, something that varies across the belt in ways that carry information about where objects formed and how long they have been where they are. The colour of a Kuiper belt object is not incidental. It is a record. Most Kuiper belt objects fall into two broad colour categories when measured in reflected light. Some are neutral in colour, grey, reflecting light roughly equally across visible wavelengths, similar in appearance to a carbonaceous asteroid or a piece of dark rock. Others are red, not subtly red, very red in some cases, redder than anything commonly found in the inner solar system, reflecting significantly more light at red and infrared wavelengths than at blue wavelengths. This redness is the colour of tholins, complex organic molecules, chains and rings of carbon, hydrogen, nitrogen and oxygen, that form when simple ices are exposed to ultraviolet radiation and cosmic rays over geological timescales. The process is slow, it does not produce tholins quickly, but given millions of years of irradiation at Kuiper belt distances, the surface chemistry of an icy body undergoes a gradual transformation. Simple molecules break apart under radiation, recombine into more complex arrangements, and the resulting compounds are dark and red. Tholins are not a single molecule. The word is a category, coined by Carl Sagan and Bishun Khare in 1979 to describe the reddish-brown residue produced in laboratory experiments simulating the chemistry of outer solar system environments. The experiments exposed mixtures of nitrogen, methane, and other simple molecules to ultraviolet light or charged particles and collected the complex organic material that formed. The result was a sticky, dark, reddish substance with a complicated molecular structure that varied depending on the starting mixture and the energy source. In the Kuiper belt, the starting mixture is whatever ice composition the surface has: water, methane, nitrogen, carbon monoxide, ammonia in various proportions, and the energy source is the combination of solar ultraviolet radiation and galactic cosmic rays. The cosmic rays are the more penetrating of the two, capable of reaching depths of a meter or more into the surface over billion-year timescales. The ultraviolet radiation acts only on the very uppermost surface layers. The result over 4 billion years is a surface layer of processed material, darker and redder than the fresh ice beneath, insulating the interior from further radiation to some degree, accumulating gradually as long as the object remains in the outer solar system and its surface is not disturbed by impact or by warming. The distribution of colours across the Kuiper belt is not uniform, and that non-uniformity is informative. The cold classical Kuiper belt objects, those in near circular low inclination orbits, tend to be very red, consistently so. The redness of this population is among the highest measured anywhere in the solar system. This is consistent with their history, formed in the outer belt, never significantly disturbed, never brought close enough to the sun for their surfaces to be warmed and refreshed, sitting in low radiation but long duration irradiation conditions for the full age of the solar system. The hot classical population, objects in the Kuiper belt with higher inclinations and eccentricities thought to have been stirred up by the Neptune's migration, shows a wider range of colours, including both red and grey objects. The scattered disk objects, which have experienced more dynamical processing, tend toward greyer colours on average. This pattern, red cold classicals, mixed hot classicals, greyer scattered disk objects, fits a picture in which colour reflects dynamical history. Objects that have been scattered, that have had their orbits perturbed, that have experienced closer approaches to the sun, have had their surfaces disturbed or refreshed in ways that reset or reduce the redness. Objects that have sat undisturbed in the outer belt have had the longest uninterrupted time to accumulate tholin-rich surfaces. There is a complication, though, and it's worth stating plainly. The colour of a surface is not determined solely by radiation history. Impact gardening, the process by which small impactors continuously churn the uppermost surface layers, can excavate fresh ice from below and mix it with the processed material above, altering the colour in ways that are difficult to distinguish from dynamical effects. A very red object might be one that has had minimal impact gardening, as well as minimal dynamical disturbance. A greyer object might have had more impactors, or more dynamical processing, or both. The two effects, radiation processing and impact gardening, operate simultaneously and in opposition, and disentangling them from colour data alone requires additional information. Spectroscopy can help. The specific absorption features in a surface spectrum can distinguish between different types of processed organics, different ice compositions, different mineral components. But spectroscopic data for Kuiper belt objects is limited. The objects are faint, the exposures required are long, and the number of objects with detailed spectroscopic characterization is a small fraction of the known population. Eris is white, almost perfectly so, with an albedo near 1, reflecting nearly all the light that hits it. This is anomalous for a Kuiper belt object, and the explanation most consistent with its orbit is surface refreshing through volatile cycling. As Eris moves through its highly elliptical orbit, approaching perihelion and then retreating toward aphelion, its surface temperature changes enough to drive sublimation of nitrogen and methane ices during the warmer phase, and redeposition of those ices during the colder phase. Fresh ice deposited from the atmosphere is bright. The cycle covers the older, darker surface with new material on each perihelion approach. Eris, in other words, may have a very red interior, tholin-rich, radiation-processed, beneath a white exterior that was renewed during its most recent approach to the Sun. The colour at the surface tells one story. The colour a metre below the surface tells another. Arakoth, by contrast, is uniformly red across both lobes, with no significant colour variation between the two components despite their slightly different sizes. This uniformity suggests the two lobes formed from the same material in the same location and have had the same irradiation history since formation, consistent with the gentle local collapse mechanism described in the previous chapter. The redness goes deep, or at least deeper than impact gardening has reached, because the impact rate in the cold classical belt is low enough that the uppermost layers have not been significantly churned. Colour, then, is not the decoration, it is chemistry, and chemistry at these distances and timescales is history. The redness of a cold classical Kuiper belt object represents billions of years of uninterrupted irradiation, the slow accumulation of complex organic molecules on a surface that has never been warmed, never been strongly perturbed, never been refreshed by the kind of volatile cycling that resets Eris's exterior. It is the colour of time, measured in molecular complexity rather than in rings or layers or any of the more familiar geological records. Whether that colour can be read precisely enough to reconstruct a full irradiation history for individual objects, the exact duration, the radiation sources, the depth of processing, is not yet possible with current data. The colour is informative but not fully decoded. Each measurement adds something. Each spectroscopic observation constrains the possibilities a little further. But the full picture of what the colour distribution of the Kuiper belt is actually saying about the formation and evolution of the outer solar system is still being assembled. The shift from certainty to something more like curiosity happens naturally when sitting with that. The colours are real. What they mean precisely is still an open question being worked on from multiple directions at once. Not all of what the belt contains moves in the same plane, or at the same inclination, or follows the orbital patterns that Neptune's influence would predict. Some objects are tilted in ways that don't fit. Their orbits lean at angles inconsistent with the belt's general structure, and that inconsistency has no clean explanation yet. In January 2019, a spacecraft that had already done what it was built to do, fly past Pluto, return its images, complete its primary mission, continued outward into the Kuiper belt and photographed an object that no instrument had ever resolved clearly before. The object had been discovered in 2014 by the Hubble Space Telescope during a deliberate search for a suitable flyby target for New Horizons after its Pluto encounter. It appeared as a point of light, slightly elongated in the best available images, moving slowly against the background stars. It was given a provisional designation, 2014 MU69, and later, after the flyby, a formal name, Arakoth, a word from the Powhatan/Algonquian language meaning sky. New Horizons passed within 3,500 kilometers of Arakoth on January 1st, 2019, at a distance of approximately 6.6 billion kilometers from the Sun. The images it returned over the following months transmitted slowly because at that distance even radio signals travelling at the speed of light take more than 6 hours to arrive, showed something that no model had fully anticipated, something that required careful examination before its implications became clear. Arakoth is shaped like two spheres pressed together at a narrow neck, not two spheres of the same size. The larger lobe, named Ultima, is approximately 22 kilometers in its longest dimension. The smaller lobe, Thule, is approximately 14 kilometers. Both are roughly rounded, smoother than expected given the assumed impact history of objects in the outer solar system, and both the same color, a uniform, muted red that shows almost no variation between the two lobes or across their surfaces. The neck between them is narrow. The contact region where the two lobes meet is indented, a collar of material that formed when the two bodies came together, redistributing surface material around the contact zone without the kind of explosive disruption that a high-velocity impact would produce. Everything about the shape of Arakoth, from the roundedness of the individual lobes to the gentleness of the neck to the uniformity of the color across both components, points to a slow formation history. Two bodies that condensed from the same local cloud of material began orbiting each other as they formed, and eventually drifted together at a relative velocity low enough, perhaps just a few meters per second, slower than a walking pace, that the contact was a settling rather than a collision. This matters beyond Arakoth itself. The shape of a small body is a record of the process that formed and subsequently modified it, and Arakoth's shape is nearly unmodified from its formation. It has not been significantly impacted since the two lobes merged. The surface lacks the large craters that would indicate a violent impact history, though it has small pits and subtle topographic features whose origins are still being analysed. The smooth lobes reflect a formation environment with low collision rates and low relative velocities between objects, consistent with the cold classical Kuiper belt's dynamical character. The uniform redness of both lobes is significant in a different way. If the two lobes had formed in different locations and been brought together by some later dynamical process, captured into a binary orbit through a gravitational interaction with a third body, say, they might be expected to show some color difference, reflecting different formation environments or different irradiation histories. They do not. The redness is the same across both lobes, across the neck, across the entire visible surface. This uniformity implies that Ultima and Thule formed from the same material in the same place at the same time, and have had identical surface histories ever since. The formation mechanism most consistent with Arakoth's properties is the pebble cloud collapse described in the previous chapter about binary systems, a local gravitational instability in a swarm of small particles, collapsing into two concentrations that began orbiting each other as they contracted, and eventually merged when their orbit decayed through tidal interactions and Kozai-Lidov cycling over millions of years. This mechanism, sometimes called the streaming instability, is not unique to Arakoth. It is thought to be a general process by which small bodies in the outer solar system formed, operating when local particle densities were high enough for self-gravity to overcome the dispersive effects of turbulence and radiation pressure. What makes Arakoth valuable is not that it formed this way, but that it preserved the evidence of having formed this way across 4.5 billion years. Most objects in the solar system have been modified enough by subsequent processes that their original formation signatures are obscured or erased. Arakoth has not been. It sits in a low collision rate environment at 44 astronomical units from the Sun, too far for any significant thermal processing, too far from other large bodies for frequent gravitational disturbances, too small to have experienced the internal differentiation that reshapes larger bodies. It is, as far as can be determined from current data, a nearly pristine record of how small bodies in the outer solar system assembled themselves in the first few million years after the solar system formed. There are surface features on Arakoth that do not yet have agreed upon explanations. Bright patches, small regions that are slightly brighter than the surrounding terrain, possibly areas of fresher ice exposed by small impacts or by sublimation-driven processes. A series of roughly evenly spaced bright spots along the neck region that have been informally compared to a necklace in mission documentation. Subtle variations in surface texture between regions that appear smoother and regions that appear slightly rougher. What drives these features, whether they are compositional variations, topographic effects on how light reflects at the high phase angles of the flyby images, or something related to the specific history of different surface regions, is still being worked out from the data New Horizons returned. The flyby was a single pass at high speed, providing a limited range of viewing geometries. Features visible from one angle were not visible from another, and the resolution varies across the surface depending on distance and orientation during the approach. The analysis is ongoing years after the flyby because the dataset is rich enough to continue yielding new detail on careful re-examination, and because some of the features are subtle enough to require careful comparison with models of how illumination, surface roughness, and composition interact at those distances and temperatures to produce the observed brightness patterns. The distance at which New Horizons photographed Arakoth is worth holding for a moment, because it reframes what the images represent. 6.6 billion kilometers. That is approximately 44 astronomical units. Light takes about 6 hours and 10 minutes to travel that distance. When the closest approach image were taken, the signal carrying them back to Earth had not yet arrived, when the spacecraft had already moved on past Arakoth and begun its outward journey again. The images that exist, that have been analysed, published, discussed, were assembled from data that took hours to travel at the speed of light, compressed and transmitted by a spacecraft drawing power from radio isotope thermoelectric generators producing less than 200 watts at the time of the flyby. New Horizons is still travelling outward. It is now beyond 50 astronomical units from the Sun, the first spacecraft to have directly observed a classical Kuiper belt object and the only spacecraft currently returning data from the cold classical belt. Its instruments are still operational though degraded, and there is a small possibility, depending on whether a suitable target can be identified within its trajectory and whether the mission is extended, that it might observe another object before its power supply becomes insufficient to return science data. That possibility is not certain. It seems, thinking about it, the repetition is honest here, like a thing worth holding without resolving into either hope or dismissal. Another encounter might happen, or New Horizons might continue outward past the belt's outer edge without another close flyby, becoming the fifth human-made object to leave the solar system, carrying no further images of the region it passed through. What Arakoth represents in the broader effort to understand how solar systems form is a data point of unusual clarity. Planetary formation models have long predicted that small bodies in the outer solar system should show evidence of the streaming instability mechanism, but the evidence in other populations has been indirect, inferred from size distributions and binary fractions and dynamical properties, rather than from the direct imaging of a single well-preserved body. Arakoth is the direct imaging. It is one object, one flyby, one data point, but it is a data point with enough surface detail to constrain formation models in ways that statistical surveys cannot. The smooth lobes, the uniform colour, the gentle neck, the absence of large craters. Each of these features, taken alone, is suggestive. Taken together, they converge on a picture of formation that is now better supported by direct observation than it was before January 2019. Whether other objects in the cold classical belt look like Arakoth, whether the two-lobed contact binary shape is common or unusual, whether the surface uniformity is representative, cannot be determined from one flyby. The cold classical belt contains hundreds of thousands of objects. Arakoth is one of them, the one that happened to be close enough to New Horizons' trajectory to be reachable with remaining fuel. It is for now the clearest window into a world that was sitting there, unchanged, for 4.5 billion years before a spacecraft passed by in a single morning and photographed it for the first time. The objects New Horizons observed, Pluto, Arakoth, both sit in regions where Neptune's influence is felt, either through resonance or through the general dynamical environment Neptune's migration created. But some objects in the outer solar system sit in orbits that Neptune cannot explain. Their paths reach so far and are so strangely oriented that a different influence has been proposed, one that has not yet been found. 6 objects. That is where it started. 6 trans-Neptunian objects with highly elongated orbits, their perihelia clustered in a region of space that, when plotted, did not look random. Their orbital planes were tilted in similar directions. Their arguments of perihelion, the angles describing the orientation of their orbits in 3-dimensional space, were grouped in a way that probability calculations suggested was unlikely to occur by chance if the only forces acting on them were the known planets. The probability estimate, when Konstantin Batygin and Mike Brown published their analysis in 2016, was roughly 1 in 14,000. That is not impossibly small, unlikely as events happen. But 1 in 14,000 is small enough to warrant an explanation, and the explanation Batygin and Brown proposed was a planet, a body several times the mass of Earth, in a distant orbit, shaping the outer solar system through gravitational influence that has never been directly detected. They called it Planet 9. The orbital clustering is the core of the argument, and it is worth following carefully because the argument is more nuanced than the name suggests. Trans-Neptunian objects in very distant orbits, objects with semi-major axes beyond 250 astronomical units, are not strongly influenced by any of the known planets on short timescales. Neptune's gravity, which dominates the Kuiper belt proper, becomes negligible at those distances. Jupiter, Saturn, Uranus, their influence at several hundred astronomical units is real but weak. An object in a distant, elongated orbit is largely free to precess, to have its orbital orientation slowly rotate in space, driven by the combined weak pulls of the known planets and the galactic tide. If that precession were the only force acting, the arguments of perihelion of distant objects should be distributed randomly around the full 360 degrees. They are not, or at least the ones known in 2016 were not. They were clustered, and the clustering was in a direction roughly opposite to where a perturbing planet would need to be in its own orbit to produce that effect. A massive body shepherding distant objects into correlated orientations through repeated gravitational nudges over millions of years. This is where the argument begins confidently, and then grows more careful as the details accumulate. The proposed Planet 9, in Batygin and Brown's original model, would have a mass of roughly 5 to 10 times Earth's mass, an orbit with a semi-major axis of perhaps 4 to 800 astronomical units, and an orbital period of 10,000 to 20,000 years. It would be far from the Sun at any given time, cold, reflecting very little light, and in a region of sky that has not yet been systematically searched at the sensitivity required to detect such an object. At 800 astronomical units, a planet 5 times the mass of Earth with a dark surface would have an apparent magnitude of approximately 22 to 25, well within the detection capability of current large telescopes, but only if pointed at the right part of the sky. The sky is large. The search area, even constrained by the clustering argument, spans a significant fraction of the celestial sphere. No confirmed detection has been made. As of the current state of the search, Planet 9 remains a hypothesis. The clustering itself has become more complicated since 2016. As more distant trans-Neptunian objects have been discovered, partly through dedicated surveys motivated by the Planet 9 hypothesis, the statistical picture has shifted. Some of the newly discovered objects fit the clustering, others do not. Some analyses of the full current sample find that the clustering is less statistically significant than the original 2016 estimate suggested, partly because the original sample of 6 was small, and partly because observational bias, the tendency of surveys to find objects in certain parts of the sky more easily than others, may have artificially concentrated the known population in ways that mimic the clustering signal. This is a genuine problem in the field, and it is being taken seriously. The surveys that found the original 6 objects were not uniformly distributed across the sky. They preferentially observed certain regions. If the surveys were biased toward the parts of the sky where those 6 objects happen to be, the clustering in the data might reflect survey geometry rather than a real physical grouping. Correcting for observational bias is technically difficult. It requires detailed modelling of which parts of the sky each survey covered, to what depth, at what time of year, and then asking whether the observed distribution of distant objects is consistent with the uniform underlying distribution once those biases are accounted for. Different research groups have done this analysis and reached different conclusions. Some find that the clustering persists after bias correction. Others find that it largely disappears. It seems, and this is a hesitation worth sitting with rather than resolving quickly, that the current state of the evidence is genuinely ambiguous. Not ambiguous in the way that fringe ideas are ambiguous, where the mainstream is confident and the dissent is marginal. Ambiguous in the way that real scientific questions sometimes are, where competent researchers working with the same data reach different conclusions because the data is not yet sufficient to distinguish between hypotheses. The Planet 9 hypothesis is taken seriously by a significant portion of the planetary science community. It is also questioned by a significant portion of that same community. Both positions are defensible from the current evidence. What would resolve it is either a detection, a confirmed observation of the object itself, or a survey comprehensive enough and deep enough to say with confidence that no such object exists in the proposed region. The Vera C. Rubin Observatory, which will conduct the legacy survey of space and time beginning in the mid-20s, is expected to find hundreds of new distant trans-Neptunian objects and will either strengthen or weaken the clustering signal substantially. It may also directly detect Planet 9 if it exists and happens to be in a part of the sky the survey covers. The alternative explanations for the clustering are worth noting. One possibility is that the clustering is a statistical artifact that, with a sufficiently small sample, random distributions occasionally produce apparent clusters, and the original 6 objects happen to be such a case. As the sample grows, this explanation predicts that the clustering should dilute toward randomness. Another possibility involves the primordial disk. Before the giant planets reached their current configurations, the outer solar system contained far more mass in small bodies than it does now. The gravitational influence of that mass, which has since been largely scattered away, could have imprinted orbital orientations on distant objects that persist to the present day as a fossil signal, even though the mass that created them is gone. A third possibility is that the clustering is real and caused by something other than a single large planet, perhaps a population of smaller bodies in distant orbits, or some other dynamical mechanism not yet fully modelled. None of these alternatives is clearly favoured over Planet 9. None of them is clearly disfavoured either. There is something particular about the Planet 9 situation that distinguishes it from most planetary science questions. The object being proposed, if it exists, is large enough to have had significant effects on the outer solar system, on the distribution of distant objects, on the inclinations of some inner Oort cloud bodies, possibly on the architecture of the Kuiper belt itself. If it is there, it is not a minor perturbation. It is a substantial gravitational presence that has been shaping the outer solar system throughout its history, unseen and uncounted. The solar system most people have in mind, 8 planets, a belt, a cloud, would be wrong. There would be 9. If it is not there, then the clustering needs another explanation, and the outer solar system beyond the Kuiper belt is emptier than the current evidence is sometimes read to suggest. Both possibilities are interesting. One is perhaps more interesting than the other, but that preference belongs to the observer, not to the data. The search continues, quietly in survey images accumulated night by night, in orbital analyses of newly discovered objects, in the slow accumulation of a sample large enough to say something definitive about what the outer solar system does or does not contain. Whether or not something massive sits in the distant outer solar system, the Kuiper belt itself is not static. The objects within it collide, however rarely. They fracture. The debris from those collisions contributes to the dust that fills the outer solar system, and that dust, along with the surfaces of the objects themselves, has been accumulating a chemical history for 4.5 billion years. What survives at that timescale is the next question. Think about what you have kept, not what you have stored or filed or backed up, but what has genuinely survived in your life, unchanged in its essential nature, from a time you can barely remember. A photograph, perhaps, in which the light from a particular afternoon is still present in the way it falls across a face. A piece of clothing worn soft by repetition. A habit of thought you cannot trace to its origin. These things persist not because anyone decided they should, but because nothing came along that was sufficient to end them. The Kuiper belt has been doing the same thing, on a scale that makes the comparison almost unusable, for 4.5 billion years. 4.5 billion years is not a duration that resolves into felt experience. It does not become real by being stated, but it can be approached cautiously through smaller numbers. The oldest living tree currently known is a Great Basin bristlecone pine in California, estimated at approximately 5,000 years old. That tree was already ancient when the Roman Empire was young. 5,000 years of continuous existence in a single organism is something human culture can just barely hold as a concept. It touches the edges of recorded history, connects the present moment to a past that feels genuinely remote. Now take 5,000 years and multiply it by 900,000. That is 4.5 billion years, approximately. 900,000 bristlecone pines, each one living its full 5,000-year life, laid end to end in time. The first one begins when the solar system forms, the last one ends now, or close to now. The Kuiper belt has existed through all of them. The frozen bodies in its outer reaches have been in their orbits, more or less, since before the first of those imaginary trees began to grow. Survival over that timescale is not the same thing as stasis. The Kuiper belt has changed, substantially. In the first few 100 million years of the solar system's existence, it was a different place entirely, more massive, more populated, more dynamically active. Neptune's migration through the primordial outer disk reduced the total mass of the belt by a factor estimated at between 10 and 1,000. Objects that are now in the scattered disk were nudged there from closer orbits. Objects that are now comets began their inward journeys. Some objects were ejected from the solar system entirely, flung outward by gravitational interactions into interstellar space. What remained after that early dynamical period was the Kuiper belt in roughly its current form, reduced in mass, structured by Neptune's resonances, sorted into the dynamical populations that observation has since characterized. The belt that exists now is not the original belt. It is the remainder, the portion that survived the early violence. And then, for the subsequent 4 billion years, relatively little has happened. Relatively little is doing significant work in that sentence, and it is worth being precise about what it means. Collisions still occur in the Kuiper belt. The collision rate is low, much lower than in the asteroid belt, which is more densely populated and covers a smaller total volume, but not zero. Over 4 billion years, even a low collision rate produces a cumulative effect. Small objects impact larger ones. Surfaces are gradually gardened and turned over by impact ejecta, mixed, disturbed to shallow depths by the continuous rain of micron to millimeter size particles that constitutes the low end of the size distribution. The interior of a large Kuiper belt object, below the gardened surface layer, is genuinely undisturbed, but the surface itself has been continuously, slowly reworked. The tholin-rich outer layer is not the original surface. It is a processed version of the original surface, built up over billions of years of radiation chemistry and periodically disturbed by the impact gardening at the smallest scales. Larger impacts, collisions between objects kilometers in size, would have been more common in the early belt, when it was more massive, and less common in the current belt. The size distribution of Kuiper belt objects bears the signature of this impact history, a population of small objects that has been continuously generated by the fragmentation of larger ones over 4 billion years of low-rate collisions. The dust that pervades the outer solar system, detectable through its thermal emission and its contribution to the infrared brightness of the sky, is the product of that grinding, the cumulative debris of 4 billion years of slow attrition. What has not changed for most objects is the fundamental chemistry of the interior. The water ice that formed in the outer solar system during the first million years of the solar system's existence is still water ice, locked in the interiors of Kuiper belt objects, at temperatures that have not changed significantly since the objects formed. The methane and carbon monoxide and nitrogen ices, where they exist in sufficient quantities and at sufficient depths to have avoided sublimation during any close solar approaches, are still present. The complex organics that formed in the protoplanetary disk and were incorporated into the objects as they accreted are still present, altered at the surface by radiation, but preserved in depth. The chemistry of the early solar system, the specific molecular inventory of the outer protoplanetary disk 4.5 billion years ago, is sitting in the interiors of hundreds of thousands of objects in the Kuiper belt, waiting, for lack of a better word, though waiting is not quite right. Waiting is too active a term for something that has no awareness of the interval it has been through. Preserved because the conditions that would alter it have not been present. The question of what survives that long is, at its core, a question about what physical conditions are required for change. Change requires energy. Chemical change requires sufficient energy to break molecular bonds and allow new configurations to form. Phase changes require sufficient energy to overcome the latent heat of the transition. Geological change, the kind that reshapes surfaces, drives tectonics, produces volcanism, requires a heat source, either from radioactive decay, or from tidal flexing, or from residual formation neat. In the outer Kuiper belt, the energy inputs are minimal. The Sun provides almost nothing at 40+ astronomical units. Radioactive decay of short-lived isotopes, aluminum-26, iron-60, was significant in the first few million years of the solar system, when it provided enough heat to melt the interiors of large planetesimals and drive differentiation. But those isotopes are long decayed. Long-lived radioactive isotopes, uranium, thorium, potassium-40, continue to produce heat. But in small bodies like Kuiper belt objects, the heat is conducted away to the surface and radiated off before it can accumulate to significant temperatures. The only energy input that has been continuous and significant over the full age of the solar system is cosmic radiation. And cosmic radiation, as noted, affects only the outermost meter or so of the surface. Below that, there is almost nothing driving change, so the interior persists. Not because it is protected in any active sense, not because any process is maintaining it, but because the conditions that would alter it are simply not present. The cold and the dark and the distance from anything energetic enough to matter. These are not obstacles to change so much as the absence of the conditions change requires. There is something in this that returns to where the chapter began. You've kept certain things not because you work to preserve them, but because the conditions that would have ended them never fully arrived. The photograph survived because nobody threw it away. The habit of thought persisted because nothing replaced it. The softened cloth because it was worn and put away and worn again without being destroyed in any of those moments. The Kuiper belt survives. The correct word, it seems now, is persists, for the same structural reason, not maintained, not protected, simply continuing in the absence of sufficient disruption through a duration that no organism and no civilization has yet approached. Whether that kind of persistence is a form of survival, or whether survival requires something more than the mere continuation of a physical state, that is the kind of question that doesn't resolve cleanly and probably shouldn't. The cold persists, the chemistry persists, the orbits continue, each one a quiet loop around a star that was younger when they started. There are objects in the Kuiper belt whose orbits reach so far from the Sun, past the belt's outer edge, past the scattered disk, into regions that don't have settled names, that they seem to belong to a different part of the solar system entirely. One of them reaches nearly 1,000 astronomical units at its farthest point and has no clear explanation for how it got there. Sedna was found on November 14, 2003. Michael Brown, Chad Trujillo and David Rabinowitz were conducting a survey of the outer solar system using the Samuel Oschin telescope at Palomar Observatory. The survey was designed to find large trans-Neptunian objects, bodies distant enough and faint enough to have been missed by earlier, less sensitive searches. Sedna appeared as a moving point of light in images taken on successive nights. Its motion across the background stars was slow, consistent with a very distant object. When the orbit was calculated, the result was unlike anything previously observed. Sedna's perihelion, its closest point to the Sun, is approximately 76 astronomical units. Its aphelion, its farthest point, is somewhere near 937 astronomical units. Its orbital period is estimated at approximately 11,000 years. Those three numbers placed it immediately outside every existing category. 76 astronomical units is already unusual. The classical Kuiper belt extends to about 48 astronomical units. The scattered disk objects that Neptune scattered outward during its migration have perihelia that typically range from 30 to about 40 astronomical units. They approach Neptune's orbit, which is what defines them as scattered disk objects in the first place. Sedna's perihelion of 76 astronomical units is well beyond Neptune's reach. Neptune, at 30 astronomical units, simply does not have the gravitational influence at 76 astronomical units to have scattered an object outward onto a path reaching 937 astronomical units. Something else puts Sedna where it is. What that something else might be is the question that has remained open since 2004, when the discovery was announced and the orbital mechanics were laid out clearly enough for the problem to become apparent to anyone who looked at the numbers. The leading categories of explanation divide roughly into two groups: things that happened early in the solar system's history and things that might be happening now. The early history explanations invoke the environment in which the Sun formed. Stars do not typically form alone. They form in clusters, regions of molecular cloud where many stars condense from the same gas over relatively short timescales. Thousands of stars in a volume of space that is dense enough for gravitational interactions between the young stellar systems to be common. The Sun almost certainly formed in such a cluster, though the cluster itself dispersed long ago, and its members are now scattered across the galaxy. During the cluster phase, the first few 100 million years of the solar system's existence, nearby stars would have passed close enough to the outer solar system to gravitationally perturb objects in wide orbits. A stellar flyby at the right distance could have lifted the perihelion of an object from a typical scattered disk value near Neptune's orbit to a value like Sedna's, decoupling it from Neptune's gravitational influence and leaving it in an orbit that reaches far into the outer solar system. Once the cluster dispersed and the perturbing star moved away, Sedna's orbit would have remained in its lifted state, preserved by the very isolation that now makes it puzzling. This explanation is physically plausible. Simulations of stellar cluster environments produce objects with Sedna-like orbits at reasonable rates. The problem is that it cannot be tested directly. The cluster is gone, the perturbing star is unidentified, and the signal of a past stellar flyby in the current outer solar system is difficult to distinguish from other mechanisms that produce similar orbits. The second category of explanation involves something still present. A massive body in a distant orbit, the Planet 9 hypothesis discussed in the previous chapter, could have produced Sedna's orbit through gravitational perturbation, operating over billions of years rather than through a single early event. In this scenario, Sedna is not a relic of the cluster phase but a body that has been slowly modified by the ongoing gravitational influence of an undetected planet in the outer solar system. This explanation connects Sedna to the broader clustering of distant trans-Neptunian orbits that motivated the Planet 9 proposal. Sedna's orbit is one of the data points in that clustering argument, though its perihelion is so high that it sits at the extreme end of the distribution, and some models have difficulty producing an object quite like it through Planet 9 perturbation alone without invoking additional mechanisms. 2012 VP113, discovered a decade after Sedna and sometimes called Biden in informal astronomical usage, has a perihelion of approximately 80 astronomical units and an orbit that reaches several hundred astronomical units at aphelion. It shares Sedna's general character, detached from Neptune, with a perihelion too high to be explained by Neptune's scattering, though its aphelion is much closer than Sedna's and its orbital period much shorter. The existence of at least two objects in this orbital regime rather than one strengthens the case that this is a real dynamical population rather than a single anomalous object. How many objects with Sedna-like orbits exist is unknown. Current surveys have detected only the two brightest, largest, or most favourably positioned for detection at the time of observation. The actual population could be substantially larger, hundreds of objects or more, sitting in orbits that have never brought them close enough to the Sun and in positions in the sky that surveys have not yet reached with sufficient sensitivity. At perihelion, Sedna is approximately 76 astronomical units from the Sun. Light takes about 10.5 hours to travel that distance. The Sun, seen from Sedna at perihelion, would subtend an angle of approximately 1.5 arc minutes. Still a disk, but a small one, less than a 20th of the angular size it appears from Earth. The illumination on Sedna's surface at perihelion is roughly 1 part in 5,000 of what Earth receives. At aphelion, 937 astronomical units, the Sun is a point of light indistinguishable from the brightest stars, providing illumination approximately 1 part in 900,000 of what Earth receives. The surface temperature at aphelion would be somewhere near 8 to 10 Kelvin. The solar wind, which defines the heliosphere, the bubble of space dominated by the Sun's magnetic field and particle flux, extends to roughly 100 astronomical units. At 937 astronomical units, Sedna is deep in interstellar space in terms of the particle environment, even though it is still gravitationally bound to the Sun. Sedna is currently near perihelion, the closest it has been to the Sun in approximately 11,000 years, and the closest it will be for another 11,000 years. This proximity, relative to its full orbital range, is why it was detectable at all. For most of its orbit, it is far beyond any survey's current reach. There is something worth pausing at in that timing. Sedna reaches perihelion approximately once every 11,000 years. The current perihelion passage, the one happening now in the geological and astronomical present, happens to coincide with the period in which humanity developed the telescope technology to detect it. If Sedna's perihelion had occurred 5,000 years ago, it would have been closer and brighter and still invisible to human observation. If it had occurred 5,000 years from now, it might still be discoverable with future instruments, but perhaps no more easily than now. The window of detectability and the window of closest approach have overlapped, by chance, with the window of human astronomical capability. That overlap is not Kizel. Sedna's orbit does not know that telescopes exist, but it is real, and it is the reason the object is known at all. This seems, on reflection, like an important thing about knowledge of the outer solar system generally. What is known is determined not only by what exists, but by where things are in their orbits at the moment observation became possible and by which parts of the sky surveys happened to examine first. Sedna was discovered because it was near perihelion and in a region of sky that the Palomar survey examined. A population of Sedna-like objects near aphelion is essentially invisible to current technology and will remain so for the foreseeable future. The hesitation before concluding is honest here, because there is no clean conclusion available. Sedna's orbit does not fit the known solar system. Something produced it, a past stellar encounter, a distant undiscovered planet, some combination of mechanisms, or possibly something not yet modelled adequately. The evidence does not currently favour one explanation decisively over the others. What Sedna does, regardless of its origin, is extend the boundary of what the solar system is considered to contain. Before 2004, the detached population, objects with perihelia well beyond Neptune's influence, was hypothesized but unconfirmed. Sedna confirmed it. The outer solar system has a population of objects in orbits that reach hundreds to nearly 1,000 astronomical units from the Sun, decoupled from Neptune, shaped by forces that are either primordial or ongoing and in either case not yet fully understood. The solar system, in other words, is larger than the 8-planet model implies. How much larger? How far its gravitational reach extends? How many objects inhabit its outer regions? What shaped those orbits and when, is a set of questions that Sedna opened more than it answered. It is still out there at approximately 84 astronomical units currently, moving slowly toward its closest approach, which will occur around the year 2076. Then it will begin its long retreat, climbing back toward 937 astronomical units over the following 5,500 years, growing fainter and fainter until it disappears again into the darkness of its aphelion, where it will spend the great majority of its 11,000-year orbit essentially unobservable from here. The structure of the Kuiper belt, its resonances, its color gradients, its binary populations, its sharp outer edge, the orbits of objects like Sedna that reach beyond any clean category, is not just the current state of the outer solar system. It is a record of how the solar system became what it is. Reading that record backward, from the distribution of objects to the events that distributed them, is what the next chapter slowly traces. The Kuiper belt is not trying to tell us anything. That sentence matters, because the temptation when working backward from structure to history is to treat the structure as intentional, as if the belt arranged itself in its current configuration in order to be read. It did not. It is the outcome of processes that operated without direction, without memory, without any relationship to the minds that would eventually examine the results. The resonances, the color gradients, the sharp outer edge, the binary populations, these are not messages, they are consequences. The difference is important, because reading consequences correctly requires accounting for the full range of processes that could have produced them, not just the ones that seem most elegant or complete. With that said, the Kuiper belt is one of the most information-dense regions of the solar system for the purpose of reconstructing its history, and the reconstruction that current planetary science has assembled from it is detailed enough to be worth moving through slowly. Begin with now, with the belt as it currently exists. The cold classical population occupies near circular, low-inclination orbits between approximately 42 and 48 astronomical units. It is very red. It contains a high fraction of binary systems. Its size distribution, the number of objects at each size, follows a power law with a specific slope that reflects a particular balance between the original accretion process and the subsequent collisional evolution. These properties are measured. They are data. The hot classical population occupies a similar distance range, but with higher inclinations and eccentricities. It is more color diverse. It has a lower binary fraction. Its size distribution is different from the cold classical populations in ways that suggest a different formation history or a different degree of subsequent processing. The resonant populations, the Plutinos in the 3:2 resonance, the objects in the 2:1 and other resonances, have orbital properties dictated by their resonance relationship with Neptune and by the dynamics of resonance capture during Neptune's migration. Their current positions in orbital parameter space constrain the speed and extent of that migration. The scattered disk, with its high eccentricity, high inclination orbits, and its lower than average red color, reflects the population of objects that were closest to Neptune's path during migration and most strongly perturbed. Each of these populations is a separate line of evidence. Each one points toward the same event or sequence of events from a different angle. Running the clock backward from the current belt requires a model, a set of equations describing how gravity, collisions, and radiation operate over time, and a set of initial conditions to test. The approach is computational. Planetary scientists run simulations of the early solar system, specify starting configurations for the giant planets and the primordial disk. Let the simulation evolve forward in time for 4 billion years and compare the outcome to the current observed belt. The simulations that produce outcomes most consistent with the current belt are the ones that tell us something about what the initial conditions actually were. The nice model, where developed by a group of researchers in Nice, France in the mid-2000s, was the first framework to reproduce several key features of the current outer solar system simultaneously. In the Nice model, the giant planets begin in a more compact configuration, surrounded by a massive primordial disk of planetesimals. Gravitational interactions between the planets and the disk cause slow outward migration of the ice giants. At some point, Jupiter and Saturn pass through a 2-to-1 resonance with each other, triggering a period of instability in which the outer planets' orbits become temporarily chaotic, leading to rapid reorganization. In some versions of this instability, Uranus and Neptune are scattered outward dramatically, passing through the primordial disk and truncating it, producing the Kuiper belt's outer edge, capturing objects into resonances and scattering others into the scattered disk. The timing of this instability has been connected to the late heavy bombardment, a period approximately 4 billion years ago, when the inner solar system received an elevated flux of impactors, recorded in the cratering record of the Moon. The Nice model is not the final word. No model is. Subsequent work has refined it substantially, and several aspects of the original model have been revised. The timing of the instability is debated. Some researchers argue it occurred early, within the first 100 million years of the solar system, rather than at 4 billion years ago, as the late heavy bombardment connection would suggest. The specific sequence of planetary encounters during the instability is not uniquely constrained by the current data. Different versions of the model produce slightly different outcomes, and distinguishing between them requires more precise observations of the outer solar system than are currently available. What the model family as a whole has established, across many variants and refinements, is that the current architecture of the outer solar system is consistent with a period of planetary migration and instability in the early solar system, and inconsistent with the giant planets having always been in their current orbits. The belt is the evidence. Its structure cannot be produced by a static solar system. It requires motion, disruption, and subsequent settling. The self-question arrives somewhere here, quietly. Is the belt being read correctly, or is the reading shaped by the models used to interpret it? This is not a skeptical question about whether planetary science is doing something wrong. It is a genuine methodological observation. The evidence from the Kuiper belt is interpreted through models, and models are constructed by minds that bring assumptions and prior knowledge to the task. When a model reproduces the observed belt structure, that is informative, but it does not prove the model is correct. It proves that the model is consistent with the observations. Other models, not yet constructed or not yet tested, might also be consistent. The history of planetary science contains several instances of models that seemed well supported by available evidence and were later revised significantly when new data arrived. The Kuiper belt's own existence was not predicted clearly before 1992. The Nice model's specific mechanism for the late heavy bombardment is now disputed. Planet 9 was proposed based on a statistical signal that has since become less clear as the sample grew. It seems reasonable, and this seems the right word here, to hold the reconstructed history of the outer solar system as the best current interpretation of available evidence rather than as established fact, which is how planetary scientists themselves tend to describe it when being careful about language. What the belt, read as carefully as current methods allow, appears to record is a solar system that was architecturally unstable for its first several 100 million years, and then settled into something close to its current configuration, which has remained approximately stable since. The transition from instability to stability left marks everywhere in the outer solar system. The truncated outer edge of the classical belt, the resonant populations captured during Neptune's migration, the scattered disk objects thrown outward during the instability, the high binary fraction of the cold classical belt, which survived because that region was reached last and disturbed least. The colour gradient across populations reflecting different degrees of thermal and dynamical processing. Sedna and its companions in detached orbits, possibly shaped by stellar encounters during the cluster phase or by a still undetected massive body. Each of these features is a timestamp of a different kind. Some record the conditions of formation, some record the dynamics of migration, some record the degree of subsequent disturbance. Together they form a record that extends from the present moment back to the first million years of the solar system's existence. Not continuously, not without gaps and ambiguities, but with enough detail to recognize the broad shape of what happened. The belt will continue to change, slowly, very slowly, by any human timescale. Objects will continue to be nudged out of the classical belt by the slow operation of resonances and chaotic dynamics. Some will become scattered disk objects, some will eventually become comets. The collision rate will continue to grind the size distribution towards smaller objects. The cold classical binaries that have not yet merged will continue their slow orbital evolution, some eventually touching, some remaining separate for the remainder of the solar system's lifetime. The Sun will eventually leave the main sequence. In approximately 5 billion years, it will exhaust its hydrogen fuel and expand into a red giant, engulfing the inner planets and dramatically altering the energy environment of the outer solar system. What happens to the Kuiper belt at that point is not the subject of this chapter, but it is worth noting that the belt's current configuration is a mid-story snapshot. The story began 4.5 billion years ago and continues for perhaps another 5 billion. What the belt looks like now, what the surveys have found, what the simulations have reproduced, what the observations have constrained, is a single frame from a very long sequence. Reading one frame carefully is what planetary science has been doing for the past 30 years. The clock the belt contains is still being learned to read. Each new survey, each new object discovered, each new simulation run adds a small amount to that reading, refining the timestamps, narrowing the uncertainties, or occasionally revising the interpretation of a feature that was previously thought to be understood. Most of what the belt contains has never been examined at all. The objects with names and orbits are a small fraction of the total population. Everything else continues in its orbit, unnamed, unmeasured, carrying whatever it carries without any record of it existing anywhere outside the physical fact of its presence. Most of it is still out there. That sentence has been true throughout this entire narration, at every point where the known population was described, at every moment when a number of catalogued objects was given. The known objects are the ones that happen to cross a survey field at the right moment, in the right part of the sky, with sufficient brightness to register above the noise floor of whatever instrument was pointed in that direction. Everything else, the hundreds of thousands of objects that have never been imaged, the millions of smaller bodies that current technology cannot reach at Kuiper belt distances, the distant Sedna-like objects sitting near their aphelia, invisible, continues regardless. This chapter does not attempt to summarize what came before. It ends instead in the same place the belt itself is, most of it still unknown, still present, still going. The known population of trans-Neptunian objects currently stands at a few thousand objects with well-characterized orbits. A few thousand out of a total population estimated in the hundreds of thousands for objects larger than 100 kilometers, and in the billions for objects down to a kilometer in size. The fraction that has been directly observed is small, very small. Small enough that the known objects are better understood as a sample, biased, incomplete, shaped by the geometry of surveys that did not cover the whole sky at uniform depth, than as a census, What a census would show is unknown. Would certainly show more objects in the classical belt. More resonant populations, including populations in resonances with Neptune, that have not yet been clearly identified because the sample size is insufficient to pick out the signal. More binary systems, most of them unresolved by available telescopes. More colour diversity, or perhaps less. The colour distribution of the full population might converge towards something more uniform than the known sample suggests, or might reveal structure that is currently hidden by a small number statistics. It would likely show objects in orbital configurations that don't fit neatly into existing categories, things that require new dynamical explanations, new populations, new questions. Every significant expansion of the known trans-Neptunian population has produced surprises. The discovery of the first classical Kuiper belt objects after 1992 was a surprise. Sedna was a surprise. The ring systems of Chariklo and Haumea were surprises. There is no strong reason to think the surprises have ended. The Vera C. Rubin Observatory, currently completing commissioning in Chile, expected to begin its main survey in the coming years, will observe the southern sky repeatedly over a 10-year baseline, reaching depths significantly fainter than previous wide-field surveys. The Legacy Survey of Space and Time is expected to discover tens of thousands of new trans-Neptunian objects, not hundreds, tens of thousands. The analysis of that dataset will take decades. The orbital characterization of newly discovered objects requires follow-up observations over multiple years to pin down the orbit with sufficient precision for scientific use. The spectroscopic characterization of surface composition requires even more observing time on large telescopes. The full scientific return from Rubin's Outer Solar System survey will be spread across a generation of researchers, each working on pieces of a dataset too large for any individual or small group to fully analyze. What that dataset will show about the structure of the outer solar system, whether it confirms the Planet 9 clustering, whether it reveals new dynamical populations, whether it finds objects in the detached population that constrain the competing explanations for Sedna's orbit, cannot be known in advance. The survey will find what is there. What is there is the question that the survey will begin, but not finish, answering. New Horizons is still travelling. It is currently beyond 55 astronomical units from the Sun, moving outward at approximately 14 kilometers per second. Its power supply, 3 radioisotope thermoelectric generators converting the heat of plutonium decay into electricity, continues to decline at a rate of a few watts per year. The instruments are still operational. The mission team continues to search for a suitable flyby target within the spacecraft's trajectory, though the options are limited by the specific direction New Horizons is heading, and by the sensitivity of current ground-based and space-based telescopes to find small objects at that distance. If a target is found and the mission is extended, New Horizons might return one more close-up image of a Kuiper belt object before its power falls below the threshold required to operate science instruments and transmit data. If no target is found, or if the mission is not extended, it will continue outward without another encounter, becoming eventually the 5th human-made object to cross into interstellar space. Either way, the spacecraft that returned the only close-up images of Pluto and Arrokoth will leave the Kuiper belt having sampled 2 objects out of a population of hundreds of thousands. 2. The sample is not representative. It is a beginning. Here is where the metaphor arrives, and it is a simple one. Standing at the edge of a large dark field at night, holding a small flashlight. The beam reaches a few meters. Within that beam, the ground is visible, its texture, its composition, whatever lies on its surface. Outside the beam, the field continues in every direction for a distance the flashlight cannot reach. What the beam has found is real. It is accurately described. The observations are genuine, and the science drawn from them is careful and well supported. But the beam is small. The field is large. The portions of the field that the beam has not yet reached are not empty, because the beam hasn't found them. They are there in whatever state they are in, doing whatever the physics operating on them requires them to do. Most of the Kuiper belt is the dark part of the field. Not dark because nothing is there, dark because the beam hasn't reached it yet. The objects in that unobserved portion are not waiting to be discovered. That phrasing implies a kind of readiness, an orientation toward the observer that doesn't belong to frozen bodies in elliptical orbits. They are simply present. Continuing, each one in its specific orbit, following the gravitational mathematics that has governed its path since the orbit stabilized billions of years ago. Some of them are in resonances with Neptune that no planetary scientist has yet identified. Some of them are binary systems whose mutual orbits are still evolving toward whatever configuration they will eventually settle into. Some of them have surface features, mountains, plains, active pits, color variations that no instrument has yet resolved. Most of it is still out there. The repetition is honest. It was true at the beginning of this chapter, and it is true now, and it will be true after every survey that adds to the known population. Because the known population is always going to be a fraction of the total. The fraction will grow. The fraction has been growing since 1992, but the denominator grows too, as models of the total population are refined and the estimated number of objects rises or shifts with new data. The outer solar system remains, in the most literal sense, mostly unexplored. Not metaphorically unexplored, actually unexplored. No instrument has examined most of it. No spacecraft has visited most of it. The objects there have never been photographed, never been spectrally characterized, never been named. What this narration has covered is a real place. The Kuiper belt exists. The resonances are real. The binary systems are real. The color gradient across populations is measured and documented. Sedna's orbit is precisely known. Arakoth's shape has been photographed. The Planet 9 hypothesis is a live scientific question being actively investigated. The Vera C. Rubin Observatory will begin returning data. All of that is happening out there and here, in the same physical universe, at the same time as this narration ends. The frozen bodies in the outer solar system are in their orbits right now. The ones in the 3-2 resonance with Neptune are completing their slow circuits. The binaries are maintaining their mutual orbits. The Sedna-like objects near their perihelia are at the closest they will be for thousands of years. New Horizons is moving outward at 14 kilometers per second through a region where the sun is a bright star, and the nearest catalogued object is probably dozens of astronomical units away. It continues all of it, whether any mind is currently holding it or not. If this is the kind of space that helps you rest, the kind of thinking that lets the day recede and something larger and quieter take its place, then it has done what it was meant to do. Sharing it with someone who might need it is the most anyone can do to keep a space like this alive. A like, if this suits you, tells the algorithm that the quiet is worth finding. The belt will still be out there tomorrow. Most of it's still unnamed, still unexamined, still going. So will you. Sleep well.